We are a lot of persons currently connected to this workshop. Of course, there are persons in the room and persons also virtually connected. You don't see necessarily on the picture of your screen. I am very pleased to introduce this workshop on machine learning methods for econometrics. As you know, artificial intelligence and machine learning are a priority topic of SCOR. And of course, it's also a priority topic of all those working on risk, also working also on tariffs, and of course, and it's a particular and a special concern for actuaries. And therefore, I am very pleased to introduce this workshop, which is, of course, a technical workshop. It's not a general workshop. And I would like to thank especially our partner, Toulouse School of Economics, especially with Stéphane Villeneuve and Nour Medahi. And I would also like to greet the other speakers, Christian Gourou. Probably many of you know Christian and have had Christian as a professor. I would like also to greet René Garcia from Toulouse School of Economics and from University of Montreal. Just I forgot to say that Gourou currently is working at Toulouse School of Economics and also at the University of Montreal. And I would like more especially to thank Dasheng Xiu, who is coming from the University of Chicago Booth, the Booth School, more precisely, School of Business. I will not say many more words. We presented this workshop, and this workshop has been expected by many of you, and I leave the floor to the different person who will present the different more technical topic you are expecting from them. And I think perhaps I leave you the floor first, Stéphane, and thereafter you can present better than myself the different speakers, which are, I should just insist on, you are benefiting today from very well, globally well-known speakers, and therefore I think we will hugely benefit from them. Thank you so much.
So thank you, Philippe. So my name is Stéphane Villeneuve. I am from Toulouse School of Economics. I am professor of mathematics. So it's my pleasure to introduce this workshop on machine learning techniques, on machine learning for econometricians. So we will see the limitation, but also the main advantage of introducing machine learning for econometrics. So I will be short because we are a little bit late, but in Toulouse it's usual to be late, so I'm very used to be late. So we will start by a presentation by Nour, a general presentation, general overview. So that we will have a more finance-oriented paper by René, a break, kind of a coffee break, and we will have a presentation by Christian on cyber risk, and finally a very nice overview of the topical research by Dasheng. Okay, so this is for the menu. I will let the floor to Nour. I will also organize timing, so I will be the referee. I am very tough on this point. And I will also organize the question session, which means that we will have, I hope, questions from the floor, but also questions from team's participants. Okay, so Noor, the floor is yours.
Hello. So it's a great pleasure. It's a great pleasure to be here. So I'll talk about machine learning econometrics, and it's really a brief overview because there are a lot of work. So I decided to talk on some specific points and neglect others. But do not hesitate to ask questions, especially at the end if there are things that I didn't mention. When asked, and believe me, in the room you have very good experts, and if I will not be able to respond. So, the first thing to understand about machine learning methods is that they are very good to estimate conditional probabilities, like for instance, to do classification, if you want to know whether a client person will, what is the probability, I mean, whether he is likely to be in default or no. So this is, machine learning methods are very good for those if you have explanatory variables and the data. They're also very good to do, to estimate conditional expectations, forecasting. That is, if you want to forecast weather or whether there will be, what would be the stock return during the next period, well, machine learning will be quite good. So, often it's the main interest in machine learning is really prediction, not estimating parameters. That's very important to keep in mind. Of course, you may estimate parameters, but then you have to adjust for a lot of things that machine learning are doing, because there are machine learning are a lot of algorithms, and therefore, if you want to do to study the statistics of the parameters you are estimating, then the theory which is actually just starting to develop. So keep in mind, machine learning is often used to do prediction, forecasting, not necessarily parameters. Now, machine learning, they have at least 3 features which are very good at, in the context of forecasting. They can handle many explanatory variables. They can figure out non-genuine nonlinearities, that they can identify complex nonlinearities, and they can handle text data and other non-structured data like images. Today I will focus only on text data. These methods could be unsupervised or supervised. What does it mean unsupervised? It means that you will do your method without necessarily having in mind specifically what you are looking for. You are not trying to do specific classification or you want to predict something. What you just to know is to have some deep knowledge of the data. Or it could be supervised. That is, so you have a specific goal in mind, and therefore you will do the corresponding machine learning method. At the end of the day, the big strength of this machine learning method is that they are algorithms, and actually many of them come from computer science. That's good. I will not talk about algorithms today, but of course it makes statistics difficult, okay? Because there are a lot of tricks, a lot of changes from a method to another one, and therefore you may have, it makes statistics difficult. Last but not least, Large language models, of course, we hear since the apparition of ChatGPT, this is a word that we see always, we hear always. Recently with DeepSeek, of course, it made the headlines. I will not talk about that. Okay. This is more artificial intelligence, even though at some point I will come back to this point. So I will talk about these 3 points. Okay, mainly I will spend some time, my time on this. Many explanatory variables. So what we'll do, the way that it will be handled is either by penalizing the usual methods, that is the usual methods like OLS, you will add a penalty. And that is actually, it has an, you can also view it as a shrinkage method, which has Bayesian foundation. That is, you are pushing your model towards some model in mind. I will talk about 3 methods, which are the most popular: the ridge, the lasso, and the elastic net. There is another approach, which is if you have a lot of variables, you will try to reduce the dimensionality of the variable. It is mainly principal component analysis or related methods. And it could be unsupervised or supervised. So let's start with the basic. We have a model in mind, the linear model, with p explanatory variables. And as usual, condition expectation of epsilon even its variables is 0. So what we, the basic estimator is of course the OLS estimator, which is defined here. You minimize, basically, this will be the fit, and you minimize the MSE of the error. And of course, you know this formula, this nice formula in multivariate context. One important properties of the OLS is that it's unbiased. It's unbiased conditionally, but also unconditionally. That's good. That's a good property. The issue, however, with OLS is that if P is large, if I have a lot of explanatory variables, then this matrix, which is P times P, and if I have n number of observation n, well, it is likely that if P is smaller than n, you may have a lot of eigenvalues who are close to 0. And therefore, when you will invert it, it will not be a good object. And of course, if P is, if you have more observation than n, then that's not doable. So this problem has been recognized in the 70s. And then this ridge regression was introduced. And the point was keep the OLS. Actually, 1 over n is here, I'm sorry. Keep the OLS, but then do a penalty of the parameter, which is basically the norm, the L2 norm of the vector times lambda. And then you can have an analytical solution for this ridge estimator. It has this formula. And now you see that initially, maybe this will have eigenvalues close to 0, but now when you add lambda identity, all the eigenvalues are shifted by lambda. And therefore, there will be a way, the minimum value will be lambda, and therefore you will be able to invert it. Lambda is a very important parameter, of course. It is called a tuning parameter, and it's positive. It turns out that this estimator, unfortunately, is biased. For any lambda non-zero, this is biased. However, the optimal one, that is the one that minimizes the MSE, mean square error of the estimator, actually has an MSE which is smaller than the OLS. So even if the optimal one will have a bias, but it will have much smaller variance than the OLS. And it will be Or in total, it will have an MSC which is smaller than the OLS. Lambda, the optimal lambda, you will find it with the cross-validation. That is, you will use the data. Well, there are various ways to do it to find out which is the optimal lambda. Then people thought, well, maybe we can allow P which will be much larger than N, or very big. And then people thought, well, I have no idea whether some variables will play a role or no, and therefore I will use them, but I will assume that many of them are irrelevant. That is, many of the coefficients are 0. So this is known as the sparsity assumption. And then what was proposed is again the OLS criteria, and now the penalty is an L1 norm. Unfortunately, this doesn't have an analytical solution, so it will be numerical. But what is not very impressive with Lasso is that actually he will put a lot of parameters to 0. And it will select if the true model is really, it's linear and it has this sparsity, it will select the right model, which is a very good property. However, because you are minimizing the norm, it is important that this L1 norm, it is important that you normalize the H's, because if you multiply H1 by 10, then you divide beta 1 by 10. And therefore, it is likely that you would put beta 1 to 0. So in order to have the control of this, it's important, for instance, to have that all the explanatory variables, for instance, have the same variance. That is, you have to transform. Again, lambda is selected with cross-validation. When people started to use this lasso, they realized that actually there was some variability, high variability in the estimators in the context when you have some high correlation among the data, which could happen. So this was in context of genes, actually. On the other hand, computationally, this is not a very friendly algorithm. While lasso or other, I could have a different power queue, people realized that they were faster in terms of computational. And therefore, people introduced, so again, they combined the two penalty. And it has good properties. But now you lose, of course, you lose this model selection, I mean, the consistency and so on. The cost of this is that now you have two tuning parameters that you need to estimate well. The sparsity assumption was maybe questionable because you may say, well, I have a lot of variables. There is no reason that many of them are 0. And then maybe you want to reduce the dimensionality of the variables. And this is, of course, an old story. And it is known as principal component analysis. In the early 2000s, Stock and Watson looked at this problem in the context of time series. They wanted to forecast macroeconomic variables. And they took a lot of variables. And they took the PCAs of these variables. And then they used them as explanatory variables in forecasting regression, in simple linear regression models to do forecasting, where they put these PCAs and the laddered values of the variable of interest that you want to forecast. And they found out that the results were very good. It was much better than any method available there. And this method becomes very popular in central banks until these days. This method is unsupervised. That is, you will always compute the same PCA, whatever the variable y that you want to forecast. Why maybe you should tailor in a better way the way that you compute this, the way that you build these PCAs, if you have some specific variable in mind. And this is known as, it's called supervised PCA, and Dashen and co-authors wrote a very interesting paper, and they show the superiority of this supervised PCA. So this is the first one. Now I'm finished with the first piece that I told you I will talk about mini-explanatory variables. Then the second piece of this machine learning is nonlinear. Nonlinearities. They have methods or they have algorithms who are very good to detect complex nonlinearities. This is a list of variables, of methods, sorry, tree regression, random forest, extreme boosting, gradient boosting, supervector regression, k nearest neighbor, neural network, and neural network actually it has a lot of variation. What is the tree-based method? Well, I have maybe probably this slide is too long, but I have a variable of interest. I have potential explanatory variables X. I could have a large number. What does tree is that it partitions the domain on the X. This partition is done step by step by using the sample. And then at the end of the day, when you have your partition, if you want to forecast what is the best predictor of y given x equal to 0, then you will basically look in which class this h0 should be. And then you will compute the average on that class. The partition is done step by step. And therefore, you really divide by, at each step, you add one class. And the criteria are MSE, log likelihood. One thing which is important at the end of the day is the number of terminal nodes. And this is the tuning parameter of this method. And you have to of course, to compute it by cross validation again. Random forest is a variation where at each time when you split, actually you don't keep all the explanatory variables, but you took a random number of these explanatory variables. And this, it helps to basically reduce the correlation between the results. So this is a tree. I have two explanatory variables, and basically what you will do is that you will split this H1 and H2 in this 1, 2, 3, 4, 5. And this is how basically you will, if your H, if you take now one person who is here in this class, the way that you will predict its Y is that you will take all those who are here and compute the average. And this is why we call it tree, because it has this formula. K nearest neighbor, this idea is very simple. You fix K, and then you have an individual I0 that you want to know what is how to classify it, in which class it should be, or what is the predictor of his Y. Well, what you have to do is to basically to find out who are the K nearest neighbor of him. So this is a distance. You call that set and 0, and then if it's classification, you have just to take the average. 1 over k is the sum of this empirical probability, actually that those people are in class J, and if it's a regression, this is just the sample mean. Again, K should be selected by cross validation. I was really surprised. I will present later a work that I did in the context of forecasting of time series. That actually I was very surprised how this K nearest neighbor was working well. Neural network, Of course, this is probably the most popular, and it has many versions. So start with one explanatory variable. Of course, you have linear regression model, but then you may want to take a nonlinear model, polynomial. So what does neural network? It doesn't take polynomials, it doesn't take monomials, but it takes a function f, and it applies to this just to the this linear form. F is called the activation function, and of course it should be nonlinear, otherwise we come back to linear. And you have several examples possible: the logistic, the hyperbolic, and this ReLU, which is now quite popular. These days, this is the function which is mostly used. If you have several explanatory variables, then you should do this. You have now H becomes a vector. This is known as a layer. So this is actually, it has just one hidden layer, but you may recompose. That is, this guy here, apply it then a new function of the similar, it will be a second layer. And later on, we'll have, I think, Dashand has this. So I presented these two things for machine learning, and now we may maybe talk about advantages and caveats. Advantages, well, the goal is really to provide forecasts and prediction. The goal is not to estimate some specific parameters. You may, but then you have to pay the cost of adjusting on doing the stat, which is not always easy. There is a lack of interpretability of the results. So in these methods here, in the list, the tree is easy to understand. Random forests, you start to be a bit, it isn't clear because you drop some variables, you put them. But then when you go, for instance, to neural network or others, then actually the interpretation of the variables, especially if you use several layers, are more difficult. And therefore, when you show that, when you find empirically that you have a better forecasting result by using some specific machine learning, understanding the origin of that gain is not always easy. Additionally, it is very difficult to impose structure in these methods, like endogeneity. We know as economists, this is something that we care about. Sometimes quantitization, we don't know how to handle quantitization, how to impose quantitization. Even in this factor, this Stock and Watson PCAs, they just put it in ad hoc way, but there is no theory for that. And it's also, we don't know how to handle restrictions like positive definite matrix. If you want, for instance, to forecast volatility matrix, that is 2 by 2 matrix, so you have 3 elements, the 2 variances and the covariance, machine learning will forecast the 3 elements separately. And then you have a data matrix, and it could be positive or no, definite positive or no. If it is not, then you will force it. With 2, it's easy. 3, dimension 3, 4, and so on, it starts to become difficult. While with a model, that could be feasible easily. Cross-validation. Several times I mentioned this. You have to find this tuning parameter by cross-validation. And it is not always easy. And this is very, very important piece. Even Dashand, you will see later, he did papers in 6 years ago, 5 years ago, but then he realized recently that he could have done a better cross-validation, and he would not have necessarily exactly the same result. So, and just pushing the button, I mean, to think that your software will do it, well, that's not really, this is, you have to be careful anyway. Now, about these nonlinearities, you know, I was really puzzled by this saying that machine learning are much better than traditional methods to do forecasting, in particular to capture nonlinearities. Because in time series there are a lot of methods. And this tree regression is actually a partition method. And this is very well, Howelton at the end of the 70s, he introduced what he called threshold model. And to make it simple, if you have in mind an autoregressive processor for DA1, but he say, well, actually, I will have two regimes, one regime and two regime. This is what he called a threshold, and therefore, it is a nonlinear model. So, I think I will skip the rest of the slide. Now, so it is really closely related to the trees, but there are two important differences. For some reason that I don't know, this threshold method focused on one variable to partition. It could be a function of several variables, but it was dimension one. While machine learning, they will partition all the variables. Now, second difference, which is related to the first one, is that machine learning, they would do it sequentially. They would do partition step by step. While the threshold, actually, if they have one variable, they have to split. They need 5 classes, so 4 parameters. They will do a global search for that 4 parameters. Therefore, it was much slower. And this threshold literature focused on statistical properties, consistency, asymptotic the central limit theorem, which were very difficult problem, while the machine learning just focused on the computational aspect, and therefore they were able to handle much more problems. So I took realized variance. This is something that I know, and then as I say, there is a popular model, R, which is here. So this is linear regression. So realized variance is you take intraday return, 5 minutes, and you take the sum of the squares for a given day. A popular model is this R, is that you want to forecast at some horizon H, 1 day, 5 days, or 22, and you use explanatory variables, today realized variance, the realized variance of the five past days, and the past 22 days. So there is overlap here. Okay? So we wanted to compare with machine learning. So we took, this is the input variables, and we used the variables that I showed previously. And what I will show you is out of sample forecast. Comparison, sorry. And this is the result. 1 step, 5 step, 22 step ahead. There are three criteria, MSE, mean absolute deviation, and click. And as you can see, machine learning always does better. But then, let's take this R and do partition. And do partition with the logic of machine learning, that is, you use several variables. You will partition several variables. So we took daily realized returns, daily realized variance, weekly realized variance, monthly realized variance, and we did partition up to 3 classes with the 3 large, maximum 3 large. So maximum is 27 classes. We compare a lot, and this is the result. For the 1 step ahead, actually we find now by doing this. Taking this R, it is now with partition, it is better than this machine learning. We were even able to improve this because we realized that there is a specific partition where you take the extremes. You first look to the extreme. You partition 98% of the monthly realized variance. And then you do some ad hoc with daily, 2 classes, and that was here. It dominates all the others. When it is red, it's the best one. When it's blue, it's the second one. But it was better than machine learning at 1 step ahead. We did our best for machine learning to do the right tuning parameters, okay? we really make attention to that. 5 steps ahead, well, results are closer, and sometimes machine learning is still better. But here, for instance, those are close here. And 22 steps ahead, that is monthly, you have again, it's a mixed. The main point here is that by taking this simple linear model, but then doing some partition to capture some nonlinearities, we were able to improve the forecasting properties, and sometimes to beat machine learning, sometimes to be less good, but at least much closer. So the point here is that whatever what you do, if you like a model and you see that it is maybe beaten by machine learning, well, maybe you should start to think about how to make your favorite model a bit more nonlinear. And one way to do it is this threshold. And that was the main idea of Howell Tong. And we can have a nice interpretation of the coefficient. Typically, this thresholding, this is the slope of the daily realized variance, if I use the R. But when I do thresholding, I split my what the realized variance monthly is low or high. When it is high, actually I reduce considerably the slope. And the other one becomes much larger. But the issue is reason when I realized variance is quite high, the slope should be small. And then here, when I added this daily thing, it is exactly what happens. Is that now with the high one, this is the smallest slope, and then this one, and then this. Now I move to the third part, which is building measures from text data. Yes. I take a very simple example, paper. So this is Baker, Bloom, and Davis. There are other examples, but I take this one. Their goal was to build an economic policy uncertainty measure. What do they did? They did what? They take 10 newspapers in the US. They were interested by economic policy uncertainty, and therefore they defined a dictionary, so a collection of words for each of these categories. For economy, they give the list economy, for policy, several ones, and for uncertainty, they put this one. And then they took the newspapers, an article, and check. If an article has a word from each category, then they count it as one. That article is talking about economic policy uncertainty. If there is no word for each category, 3-1, they say, okay, this paper is not related to that. This article is not related to that. So they did it by monthly for the 10 journals. Then they homogenize. They say that they force that the empirical variance of each of them is 1. Because, if you have the journal, Wall Street Journal, clearly he will have much more papers about EPU than the Boston Globe, which is a regional journal, and we'll talk about a lot of things, not only econ. And then after this homogenization, they take the variance, they take just they take the average of the 10 measures, the 10 monthly measures of the 10 journals. And in order to keep in mind what is the level, they say, okay, on average, it is 100. So if it is above 100, it is above, if it is above 100, it means that it is above the average. If it is below, then it's below. And then they compare it to VIX. For VIX is Black-Scholes implied volatility, as you know, or from options for those who know. And then from the Chicago board, actually, this is the market where these options are set in the US. And you can aggregate all this implied vol, and you get this VIX. And this is really a measure of fairness, which is now used. So they compared their measure, and the good news, look, it's not exactly the same, but we see that there are really strong correlation. Actually, the correlation is 58%. So they were very happy with that. But then they thought, okay, VIX is available since 1990. Before there was no VIX, but then, however, these newspapers were there, and therefore they were able to build now this EPU measure since 1990. So over 15 years. And they spot all the important events here. And they used this measure for in other countries. So they were very happy with that. Of course, you can use it for countries who do not have VIX, like France, China, India, and they did it. Now, with this measure, what to do? Well, you don't necessarily need to do machine learning. You can use it just as an explanatory variable or as a dependent variable. This is what is done. You can also do the same type of method for to estimate other objects of interest, health policy uncertainty, national security policy uncertainty. So these two were in the same paper by Baker. You can do sentiments. Sentiments, this is Dashen will talk about it. This is something which is highly used in finance, financial data. And also this geopolitical risk measure with this paper. So they build with the similar approach, geopolitical risk measure, and then this is international. Before, this was mainly US, but here now it's really international, and this is a measure which is used a lot. So if at some point you are interested in something, you don't have the data, well, you may think about going to newspapers and so on and try to build such a measure. That's the point of this. Conclusion, well, machine learning methods are very good for forecasting. They can handle many explanatory variables. They capture complex nonlinear relationship. They can handle text data and build measures. However, one has to be very careful in the computation of the tuning parameters. Machine learning methods are really not designed to estimate well parameters. You can, but then you have to really adapt well the statistics. Imposing structures is difficult. And about this nonlinearities, if you have a favorite model that you like, you understand well the interpretation and so on, and it's easy to explain it to the regulator or to your boss or whatever, well, maybe you could just do some twist for your model and make it nonlinear, for instance, by this threshold. Thank you.
Thank you. So do we have questions from the audience? Don't be shy. You can ask any type of question. I have one, and I'm almost sure it's not a smart question. So, in fact, I have two questions. Okay, great.
Yeah, I have just curiosity, a small question on my side on the last part of your presentation on the exactly on this type of model.
Yes. Measures, not models.
Sorry, measures. Yeah.
This is how it is. Yes.
So it's a way to, yeah. Would it be also, would be possible to use it to predict or
yes.
that, okay.
Yes, so actually in this paper, so VIX was used to predict, for instance, stock returns and so on. So in this paper, they show that this measure helps to predict, and they put the two variables, okay? Both the VIX and this EPU, and actually they show that both were helping to predict, which means that this EPU has some information that the VIX doesn't have. And the VIX has some information that this doesn't have. But yes, it is very useful. And now it is used a lot. It is used in structural VR, in macroeconomic, and so on. So you build it, and then you can use it for either as an explanatory variable or as a dependent variable. Okay.
Maybe I can add something to the answer I know. If you have this kind of data coming from the media, okay, these are text data, so you can use it for prediction purpose. If you are using for prediction purpose, this is not only with the idea of predicting, this is with the idea of managing your portfolio. So it will have an impact on prices. And so maybe after the evolution of the prices that you will see are in fact based on the media. And so you have an equilibrium, and maybe we not know what will arise. Okay, we will have the effect of media everywhere, and you have a change also on the sentiment of people computed from the media. So this is more complicated than that. All right? But you can do it, you can try in short run. Okay.
Yes, Stefan.
Another question from the audience? So can I ask my stupid question? Maybe? So in fact, I was very happy to listen your overview, because in part you answer this question. So, but I was curious about the following. So we have plenty of case studies, econometrics, standard traditional methods to do policy recommendation. Is there a neural network method that, so assume that you take, as you did for predicting variance. So you take a paper which apply a traditional economic method from it for econometrician, a standard linear one, whatever, and you have a policy recommendation. So now you change your mind and you use a neural network method. Can we imagine that we change the policy recommendation by far?
Well, I don't know whether it's possible to change by far, but so author of Dashand, Brian Kelly, he has a recent paper where he used these neural networks in the context of portfolio, I mean, pharma French, and these factors. And he finds a lot of factors. All these neural networks will basically they build this stochastic distant factor. What is the sharp ratio maximal out of sample you will be able to make? Well, it is quite huge, but for the moment it's not implemented. Okay. Because it's not necessarily easy. And I guess in terms of policy, you know, at some point the policy makers will need to understand exactly what does it mean, this machine learning. What is the recommendation? So, and this is in terms of interpretability, this is for the moment, I'm sure that there are places where it is used, like in medicine, you know, if you want to detect what are the genes who are playing a role. But in policy, maybe it is more difficult, but maybe, I don't know all the examples, to be honest.
So before letting the floor to René, I have a question from the external audience, or just to summarize, in the newspaper example, isn't it spotting isolated keywords in newspaper a bit simplistic?
Yeah, that's correct. So actually, this is what I wanted to say. I forgot. So this is what is done, and it works well. Can we do better? Well, so Dashand has in his presentation an example where clearly the same word could be confusing. So it was the raise. Raise, apparently, people take it as a positive. So in the context of sentiment, they take it as a good, the sentiments are good. So if you look only to the word of raise, then you may think that that paper has a positive sentiment. However, they used LLM, and LLM. So he told them, well, actually, that was not the case because there is the context. And it turns out that one of the examples that Dashand has is that there was a raise of concerns, and therefore, actually, that was not positive sentiment, but negative sentiment. And clearly, yes, there is probably this measure could be improved probably by taking more sophisticated things, by taking context of the word and so on.
Okay. Thank you a lot, Noor. I think it's time to let the floor. René.
So my name is René Garcia. I am a professor at the University of Montreal and an associate member of the Toulouse School of Economics. And it's a great pleasure to be here today to talk about optimal portfolio allocation and deep learning. So why should we use machine learning in portfolio allocation? So let's define very generally what portfolio allocation is. I mean, like basically you want to allocate wealth optimally between several assets in pursuit of a financial objective. Of course, you can have a simple model to do that, but if you consider that you want to allocate this wealth dynamically, if you want many assets, if you want constraints on the shares, or if you want to introduce transaction costs, well, then analytical solutions are not possible. And then you want to use numerical methods. Now, standard numerical methods has finite difference. Basically, finite difference, you construct a grid. But then when you have many of these things, the grid becomes huge. And so curse of dimensionality will prevent you from doing that. So what I'll do today is to try to see how machine learning and deep learning in particular can overcome the numerical challenges implied by complex models. So my outline, first I'll start with the regularized regressions. So it's very in line with what Noor has mentioned at the beginning. And then I will introduce reinforcement learning, which is a very general way of approaching dynamic problems and making decisions in a dynamic context. It's much more general than finance. It's applied to many disciplines. And then I will introduce, to finish, so-called theory-informed neural networks, which is inspired by physics, which has physics-informed neural networks. And it goes some way to get neural networks that can be constrained by some theory. Okay? Noor was mentioning that we have to make a link between theory and machine learning, and this is one way to do it. So it's very new. I mean, like it's not there are not many papers in finance or in economics, but it's starting to be important. And then I will take a perspective with respect to machine learning. I mean, I will repeat some of the things that was mentioned. So it's problems with machine learning, the potential solutions, and then I'll conclude with the main takeaways. So when we think about portfolio optimization, we think about the classical portfolio optimization, the Markov 1952, so it's quite a long time ago. And so basically what we have one period return on n assets in excess of the risk-free rate. The variables are the IID normal, and they have first and second moment and sigma variance covariance matrix. So basically the investor, what he has to do is to maximize the expectation of his utility with respect to the shares he will put in the different assets. And the problem that he will solve is the shares times the vector of returns, and he will penalize by minimizing the volatility. There is a minus sign here. There is a gamma, which is the risk aversion. And then that will be the shares, the variance of the portfolio. So if you know the distribution, you know the mu and sigma, it's easy. You can write the solution, omega star, 1 over gamma sigma minus 1 mu. But most of the time, you don't know these parameters, so you have to estimate them. And so you can rewrite exactly the same formula with little hats. And then, that will be you'll have an estimation problem, and then you will plug the values that you have estimated in this formula. Now, as you can see, it's a very stringent optimization structure, very limited. And as Noor mentions, there is a problem here of estimating means and variance covariance metric of asset returns, especially if you go in higher dimensions. So regularized regression is a way to go. And here I will borrow from Dasheng with Kelly book. And I will write the Markowitz plugin solution. In this regression, it will be the OLS coefficient in a regression of a constant vector on the sample asset returns. Okay? And so the OLS solution of this problem, will be omega hat proportional to the plugin solution that we have with the coefficient here estimated by this formula. Now, if we want to enter dynamics in this context, we can introduce information that we have on the assets that we consider. The assets that we consider, if they are stocks, we know a lot about stocks in terms of the capital ratios of the firm. You have also the capitalization value. You have the investment, the profitability of the firm. You have a lot of information about firms. And so Brandt and co-authors introduce a dynamic weight. And this dynamic weight is a set of characteristics times the beta. And so now the new formula that we'll have here will be the beta prime times this ST minus 1 RT. And then I will consider the product of these characteristics times the returns as a new factor. And then the estimated portfolio coefficient will be the covariance of these factors, minus 1, times the expectation of these factors. So basically, I have introduced dynamics into static regression. Now, if we extend to a very large set of assets, then I can use a ridge regression that Noor has introduced in the first talk, or I can go further and take the original signal, the XIT that I have on the problem, the returns, and I can introduce now a function of this original characteristic to transform them into nonlinear characteristic through a neural network. So you have the XIT in the light blue, and then you transform them through a layer of neurons into nonlinear variables, and then you have your weight as beta prime times these characteristics estimated through the neuron. And then the regression becomes beta prime ST minus 1 theta, and then theta are all the parameters that Noor introduced that constitute the neural net, okay? The function that he had, the alphas and the betas enter. So it's a very large optimization because you have all these parameters, but with algorithms, you can find the solution of this problem. So this is what we start with, like a simple regression with a very constraint model, and already through the regression, you can generalize the problem and introduce machine learning in a regression context. Okay? So the second method, reinforcement learning, as I said, is a very general method to make decisions in a dynamic context. And reinforcement learning means that through your actions, you will be rewarded or you will be penalized, okay? And if your action is good and you receive a good reward, well, you will continue with this policy or with, if not, then you will tend to change, okay? But that's like a dog, you know? I mean, if he has good behavior, you give him a treat. If he doesn't behave, you don't give him a treat. And so he learns. And that's exactly what we have here, okay? So basically, you have an agent that who observes an environment, and this environment is described by states. So in the context of portfolio allocation, it would be the current stock prices, the current portfolio values, economic conditions, and then you can put whatever on here. And then this agent, based on this state, has to make a decision, and it takes a particular decision A, the amount of shares of a particular stock that he wants to buy or sell. And for this, he receives a corresponding reward G, which will be the return on the current portfolio or the utility of the current wealth. And then he will transition to a new state. So basically, the goal here is to learn what actions maximize the total reward over time. In other words, you want to train the agent in a way that when he observes any state, he will know what's the best way of acting in that state. Contrary of...
René, don't you mind if I ask a clarifying question? So the transition is unknown, right? You don't know.
For now, I mean, I will talk about the transition.
Oh, sorry.
The probability, the transition probability. You can know them or you can learn them.
Okay, sorry.
Okay. Okay. So, contrary to the mean variance approach that we have seen, you can optimize a policy that will select the portfolio weights without computing the mean and the variance. Okay? So we don't have to estimate those statistics, and that's useful in a way. And then you train your algorithm on a set of historical data to learn an optimal policy for selecting portfolio weights. And the state transition will be either model-based or model-free through trial and error. So that's your answer. Now, once you have learned the policy, the optimal policy, then you can use this learning to do the allocation to the assets in real time based on market conditions. So basically, on a set of historical data, you learn the optimal policy that you have to apply. And then on the validation period, in real time, you will apply this policy, and hopefully you'll get a good reward. But, I mean, it's a bit like when we do estimation and forecasting. I mean, like, you know, you want to have an out-of-sample validation of what you have learned. Okay, let's be a bit more precise about the environment, the policy, the reward, and the objective. So basically, you have a Markov decision process. So you have states, you have actions, and you have the transition probabilities between the states based on the past state and the actions that you have taken. So after that, you have to decide how to determine the share that you will allocate to each asset based on on the conditional on the state and the action you are taking. So this could be either deterministic or stochastic, this policy. And then the rewards, basically, in all generality, it will be what you have collected over time, from time small t to big T. And you will have all the future rewards that you collect, and then you discount them with a parameter. And finally, the goal of the agent will be to maximize the J function of the policy, which is the expectation of the sum of the discounted expectation of the future rewards. Now, I will start with a general definition. Basically, I will start with value function. And that's kind of, I take here the definitions with dynamic optimization. Okay, it's really, reinforcement learning is really constructed from dynamic optimization, Markov processes, and dynamic optimality. Okay, so you have a value function of a state based on the policy, and that will be the total expected reward obtained by starting from a specific state, ST, and then following the policy pi over thereafter. Okay, so this is the formula here, and you can see that this value function depends essentially on the states. But you have another value function that depends on both the state and the action. And that will be the conditioning now of these future rewards will be on ST and AT. So it's a double conditioning. Now, in dynamic optimization, dynamic programming, Bellman equation is a very important concept. Basically, it gives you the value of a current state and the relation between the value of a current state and the values of the successor states. Okay, so you have this kind of recursive formula where the value of a state is the expectation under the policy of the reward that you'll get in the next period plus gamma, and then you have the value function at the next state. And then the same for the Q function. And then basically, optimizing the reward will be optimizing, you have the Bellman optimality equation that you will get, and that will be the maximum of this V pi or Q pi. Now you will maximize the action, choosing the shares, and then you will sum over all the states, basically through the transition probability that you have, I mean, or you estimate, and then you will have the recursive formula with now the optimal function here. Okay, so that's definitions and optimization. So where does machine learning comes in? Where? Now if you have a problem like that, it's really a very complex problem. Okay? So dimensionality of the problem may impair this optimization. So you cannot solve it easily. And that's where deep learning comes in. Deep learning networks are used as function approximators of these optimal value functions and the optimal policy distributions. Okay, so now the two value function I defined before, the V and the Q, will be neural networks with parameters, omega, and then the policy will be pi, and the policy will also be a neural net. And often what people do is the policy that's frequently chosen for stochastic policies is this policy pi of theta, which is obtained by selecting the action from a normal distribution where both the mean and the variance are also neural networks, okay? So you have a set of neural networks embedded that will give you, so it's not an easy problem, but at least you can solve it. And now you have to define this algorithm to find a solution with these complex objects. Okay? So basically, there is a general type of algorithms that's called actor and critic. I mean, I'll give you some vocabulary that attach to this reinforcement learning. Whatever discipline you work with reinforcement learning, you will find this critic and actor terminology. So basically, the critic estimates the value of a state and possibly evaluates how good is the chosen action. And then the actor will update the policy in the direction suggested by the critic. And so the two won't necessarily agree. And so one may have an advantage compared to the other. And the advantage function is a difference between the Q and the V. And the Q is conditioned on S and A, and the V is on ST. So in a sense, I mean, like, this is what you gain by having the action, by taking the action according to the policy. Now, often this Q is a bit difficult to compute. So there is an unbiased estimator of these things called the temporal difference, which relies only on the V and a difference of the V between two states in T and T plus 1. So an illustrative algorithm will be to take this temporal difference, but instead of taking at one period, I will take it at n period. And then I will compute the losses according to L theta and L nu. Those two losses are associated with either the n-step error and the log pi theta is a policy error. And then you will update your parameters as you go along. Okay, so that's kind of, in a nutshell, something that's very, very difficult to learn, but at least it gives you all the steps from approximation to optimization and to algorithms to implement this neural net. I will give you an illustrative example, very simple, but it shows, you know, what you can do with these methods. So you have an investor at an horizon of T and an initial wealth of W0. There are no taxes, but there may be transaction costs. The portfolio consists of n stocks, and the investor observes a state vector or a matrix containing closing price of stock at time t, potential additional information as volume of shares, covariance metrics, technical indicators, macroeconomic factors. You choose what you want, and you can put that as conditioning information. And then the objective I will choose is minimum variance, maximum returns. And then in that case, I will put proportional transaction cost, mean variance optimization with proportional transaction cost. And then in this very simple example, I drew 4 randomly selected stocks from Dow Jones, Cisco, IBM, TRV, and Walmart. I take a long sample, daily returns, from 2009 to 2020, but I use all the information until 2018, and then beginning of the first day of 2018, and then I'll use the last part of the sample to validate, okay? So I estimate the neural nets before, And here, those are the statistics associated with the trading period, meaning the one where I will validate the model, okay? So you can see right away that TRV and WMT seems like good deals in the sense that on this particular subsample, they have, I mean, for Walmart, for example, it has the highest mean and the lowest variance. And then TRV has also, compared to the other two stocks, Cisco and IBM, a lower variance and a better return, okay? So basically, I do the allocation with max ret, min var, and min var, not the minimum variance. And here, the objective will be the minimum and variance with a risk aversion parameter for the variance. And so, while I don't want to enter into detail, but often you will find the Walmart and TRV as chosen stock and where you will invest more than the other. Okay, so I mean, at least it seems to make sense. And then I compute the cumulative returns with this allocation. And well, all I can say is that all these allocation to 4 stocks, even with transaction costs in some cases, do better than the passive portfolio to buy the Dow Jones, okay? So that could be, you know, illustrate maybe what you can achieve with this method. You can get signals that, you know, you will not get by buying the Dow Jones. But I don't want to be too optimistic. I mean, like, it's just an illustration and a very simple illustration. Okay, I want to conclude my talk with something that's very new in the sense that when you go to continuous time, you can transform this optimal control problem, dynamic problem, into a partial differential equation by Ito's lemma, continuous time. And so you have so-called the Hamilton-Jacobi-Bellman equation. And these, again, I mean, like, are very hard to solve with usual numerical method, but that's where the most papers are doing. And if you have more state variables or more assets, then it becomes a bit problematic. So we cannot find analytical solution. So basically, let me characterize again this problem as a very simple problem. So you have one risk-free asset and one risk-free asset. And then the risky asset has mean mu and variance sigma. And your wealth, the diffusion for equation for your wealth, the stochastic differential equation for your wealth, will be this equation where pi will be, again, the share that you put in the risky asset. So if you write the Hamilton-Jacobi-Bellman equation of this problem, it will be given by the first equation. And then you will have the value function here at the end, at big T, will be the utility of the wealth accumulated. So if you take the first order condition of this equation, then you'll have the optimal policy, the pi star, and it will be characterized by the first derivative and the second derivative of the value function, okay? And so if you plug it in now into the HGB equation, then you will get this solution. So basically the idea here, and we know analytically the solution of this problem because it's a simple problem. So the idea here, it will be to use a neural net to approximate the value function and to see if it's capable of finding the analytical solution. So that's the solution, the analytical solution. And so for the neural net, basically it will be an approximation of the J function. And then I will characterize the loss here as a mixture of the loss that I do on the partial differential equation and the loss that I do on the terminal value, okay? Because in a sense, I mean, like, you have to control also for the terminal value and for the dynamic through the PDE. And so basically, I will write my solution for pi as the same one as I had. Instead of having J, I have the neural net, okay? And I put all the parameters that I used at the last slide. I won't go through it here. But basically, I chose a risk aversion of 2 and a mu of 6% annually, a risk-free rate of 1%, and a sigma of 20%, which is about the number for the US stock market. And here I compare what the solution in blue, I mean the dashes are the analytical solution, and the red is what we obtained by this neural net. Of course, I mean, like, it's simple, but behind this simple example, there is a lot of work to construct this neural net and the algorithm. But also, I mean, like, there is a lot more work to do through, you know, the weights that you put here, okay? Because those weights here are fixed, okay? And, you know, you can choose them or, but in fact, I mean, like, you know, the weights should be dynamic because the loss, as you move dynamically, the loss could be more on the PDE than terminal. As you approach the terminal, maybe the loss in the terminal will be more important. So there is work, and my PhD student is working on that also. But the interest of this method is that at least we constrained the neural net by some information that we have about problem. And this comes from theory, okay? So at least it guides and it answers partially the question about, you know, it answers partially the question about, you know, interpretability, or, you know, at least we have some theory where we can constrain the model, okay? Okay, I will skip this one. So problem with ML in portfolio decision, well, it could be the data in the sense that you have short time series relative to cross sections. Neural nets and reinforcement learning may be difficult to interpret. And then there is, of course, the trade-off between model complexity and interpretability. And then explainability. I mean, like, at the end of the day, you have to talk to portfolio managers. No, to talk to investors. The portfolio managers have to talk to investors, and they have to explain to them why choose Let's participate.
Thank you, René. So, same question. Do we have questions from the audience? Or checking that no question? Yes, good.
Yes, thank you for your presentation. Just as how to say, I'm not really expert in this domain, but I have curiosity because I remember in school where our professor said instead of handpicking the like your portfolio, like whatever you want, just choose S&P 500 and you will get. I don't know if it's true. I like over time, actually, the return is higher than just like you random picking the one. So I don't know what's your opinion about it.
Depends how old you are. My age, I may miss. So, and then 15.
So
I have accumulated capital and I cannot.
What René is saying is that when you are young, don't invest in Bitcoin, okay? And also when you are old, okay?
But it was a good advice.
So maybe I have a cheeky question for fund manager. So speaking about explainability, okay? Because, okay, without machine learning, we have the same explainability problem. So we have an investor that who don't know the Merton model, and you explain, oh, you have to buy S&P, so you have to allocate, you have to diversify. So do we have,
It's a little bit easier in a sense. I mean, like you can talk about what I talked just now, and then the variability, and then how long you have in front of you, you know, so.
So if I believe in.
So these principles will be the same.
Yeah, but if I believe in this principle, I believe in it. So why do I care about the machine learning method explaining me that I have to break this principle to invest in.
Portfolio managers or pension funds have also a very long list of assets. You know, it's not simply, so there are some investors that have more assets to invest in.
So if I understand well, there is this principle, and now the job is to select a part of the asset in order to replicate this principle. And this is where machine learning may help. This is, I am back to my question about transition.
When we have very difficult and because of the match. This is one way to, of course, the complex object.
Speak to the mic.
Oh, it's a complex object. So, I mean, like, but until now, I mean, like, we did not have very good solutions for large problems with all the tweaks that I hit, you know, about the transaction cost, I mean, like, all these things. Here you can enter the constraint, the transaction cost, and then search among all these possibilities, the optimal solution through these algorithms. But of course, I mean, the algorithms themselves, I mean, like, you can choose from many algorithms. So it's not an easy,
Yeah.
that's why it's trickier than to explain that than first problem.
Thank you, René. Are there other questions? So if no questions from the, so I propose to do a short break in order to recover after two nice and beautiful talks. And I think it's, I do not remember how long it's. Yes, we start at 4, yes, 30. So thanks a lot. Okay, so it's time. It is time to start the second session of the afternoon. So we have the pleasure to welcome Christian Goyerou, who will speak about cyber risk. So I will not give you all the title. I will let Christian presenting his talk. Thank you, Christian. 40 minutes.
So thanks a lot. So the organizer asked me to speak about cyber, and in particular, the potential use of machine learning techniques for analyzing cyber risk. In fact, when you have such an applied analysis, you have several steps that are several components that are very important. The first one is to explain what is the object of interest. This is not the same if you want to construct a sentiment, for instance, index of sentiment concerning the fear of cyber attacks, for instance, or if you want to design a special insurance contracts, or if you want to price, or if you want to predict, this is not exactly the same kind of problem. After, we have to look for data, or even in this case, we will see to construct database, okay, which is something complicated, and if possible, harmonized database, standardized one, okay, and rather clean. So this is something which is very important. This is a part of supervision, which is the standardization of a definition, standardization of a kind of data on which you can work, and transparency, maybe to share the data and this kind of thing. Okay? The next step are simply for the parametric modeling. This is parametric, even if you have a large number of parameters. And after you have this part concerning, I will say, the inference. Okay, you can learn, you can call it learning or estimation, but this is this part. Okay, and in general, the estimator cannot be computed in a closed form. Okay, and so you have numerical algorithm, which is something very important here. In particular, if you have nonlinear models, and if you have a large number of parameters. Okay? Maybe you know, likely you know, that last year you have a Nobel Prize in physics, okay? But it was not really in physics, it was in machine learning. So this is Jeff Hinton from U of T, from my university. If you want to meet him, this is rather easy. Okay, you have to go to St. George Street, okay, go in front of the Art and Science building, and then at lunch, you will see him at a food truck, okay? So go at a food truck, and you will see him at this place. So what he has done is something which is mathematically very, very simple, okay? This is an algorithm. It is called backpropagation algorithm. It underlies a lot of this kind of machine learning techniques. And this is a kind of algorithm which is used when you have some particular architecture in your model, which are recursive types, special recursive type of architectures, and with special parameterization. So they are known under different names. Okay, you can see neural network. You can see machine, for instance, when you have Boltzmann machine, this is this kind of thing. You will see normalizing flows, or you will see state space models. We are looking for this special architecture, okay? So they are together with the algorithm. This is a point which is very, very important, okay? Since when you are looking to the usual statistical theory, we are interested in the what is called statistical efficiency. We want to have accurate results, okay? But now there is something else, which is numerical efficiency. That is the cost, the numerical cost has to be controlled. And so there is a kind of trade-off between the accuracy of a model and the cost, okay? And we have seen before in the discussion, for instance, that likely the cost is something very important, okay? So you know, of course, that for ChatGPT, it passed from $20 to $200, okay, which is 10 times, okay, which is a lot. And you know now that you have a new computing software, which is almost for free. So there is a problem of cost. So this is very important, okay? So cyber, this is a new risk, So it is very difficult when you have to consider a new thing arriving. You have different difficulties. The main one is that we don't have data, or not a lot, okay? And the data are not under the required form for statistical analysis. They are not very reliable. So as you know, you have misreporting. You have firms that don't want to report since maybe they have paid, like the hacker, or maybe for reputation results or this kind of thing, okay? Another problem that we have is that this technology and the type of cyber attacks or cyber threats are evolving very, very fast, okay? So you have a lot of non-stationarity, and so you have to adjust your data, you have to adjust your method rather quickly, okay? And there is something else which is related to this kind of network, which is the fact that usually in insurance, okay, we have this assumption of independence between, I will say, the contracts or something like that. And here, for the attack, this is highly connected, okay, since the computers can be connected, the system of computers. And so you have network effects that are very important to take into account. Okay? But you have some other things. The analysis has to be performed not only at an aggregate level, but at the level of a firm, and maybe of 2 firms or 3 firms of industrial sectors. We don't know if the notion of firms itself is not well defined. We don't know if the individual is a firm or if the individual is a system of computer, which is not the same, okay? And not at a very aggregated level. This is not the idea. And there is something else also that we have already seen at the beginning of the development of a methodology for credit risk. Okay, for credit risk, this is not the first time there is a kind of new risk. Okay, for credit risk, we have also a problem of data, since it was not the same. We have already data for credit at the beginning, so some years ago, 20 years ago, we have already this kind of problem, simply since all the banks were withdrawing a lot of data when the credit was finished, okay? And they don't have to do that, okay? And so at the beginning, we have no data that were reliable also, okay? And, but also what we have seen is that it is very important to distinguish the occurrence of the attacks, the fact that you have is a cyber attacks on a given firm, and the severity of a cyber attack, okay? And so something which is important we will discuss also is, this is a part of the supervision, this is the standardization, including the names, okay? So for default risk, okay, you have PD, probability of default. Here, this is probability of attack, okay? You have a severity of a cyber attack. It was loss given default. Now this is loss given attack. It's all right? You can see we have put PA and not PCA, probability of cyber attacks. Since PCA, you have seen, is a principal component analysis. So we are not taking the same acronym, an existing acronym with another name. Okay? And so something that we will see is that we have almost not very good database on the occurrences, but on severity, this is much more complicated. In particular, since to evaluate the cost of an attack, in general, it takes a very, very long time, okay? Maybe you can have a hidden cyber attack, and maybe it is revealed a long time ago, okay? You don't have to reveal immediately that you are attacking. You have to stay hidden, okay? And what is important is the study of the price of individual contracts, okay? But we don't want to see immediately the contract on one firm. You will see we will maybe interested to have a contract of 2 firms together, 3 firms together, okay, to take into account the connection between firms or the connection in an individual sector. And so it is important also to conceive the possible derivatives of cyber attacks that can be at some time introduced on the market, okay? So in the terminology here, this is an example of insurance-linked securities. This is the equivalent of CDS, credit default swap, but written on several heads, okay? 2 heads or 3 heads, and more generally, basket derivatives written on S firms. So you consider a subset of S firms, and you consider, for instance, what are the firms in the set that have been attacked, or the number of firms that have been attacked. Okay. So the presentation. So we will focus on the occurrences. Okay, since severities we have no data at all, and in general we are starting by the analysis of occurrences. We will consider, it is based on different papers. We will see that what is the kind of basket derivative I can introduce, the derivatives themselves. So this is a paper with also you can see Yang that has been in the at SCOR some years ago, likely a time ago. And in fact, when you consider the S, the number of firms, all of them are not attacked. So you have stochastic subset of firms that are attacked. So this is random sets, okay? So we will see the risk of random sets. And we will also consider the prediction, and you will see so for the prediction how we will do, okay? The next section, I will discuss the taxonomy, okay? This is something which is difficult. How to distinguish and name the different types of cyber attacks, okay? Which is not easy intuitively, okay? Since we don't know if they have to be defined by the type of attack, the technical type of attacks, or the reason for the attacks, on the source of attacks, is it a Russian guy or a Chinese guy, for instance, something like that, and so on, okay? But what we can do after is to analyze the data that we have. So there is a database that exists. It is not very clean, okay? But this is the database existing currently and regularly updated and used in academic work. And after, which is maybe the most complicated thing, which is the random sets, okay? And I will explain how to define stochastic dominance very quickly on random sets, which is not easy since on set you don't have the total ordering. And there is another, historically, another case in which we have new risk, which was when we have introduced a long time ago now derivatives, okay? And before the introduction of derivatives, you have something which is called the Black-Scholes formula, okay? That is a pricing formula for derivatives. Of course, this pricing formula is completely wrong, okay? But it has a simple closed form expression, okay? And since it existed, it has been used as a consensus for people to have a first pricing and to create the market. So if you want to create now the market for these derivatives written on cyber attacks, you need closed form pricing formulas, okay? And this is what I will explain. The models for pricing are based on a kind of multivariate distribution for binary variables. This is something which is used also in the machine learning literature, but for another purpose, and which is called the law of determinantal point process, LDPP. Okay, so you will see some acronyms. So I have discussed the difficulty to have the list of names and the list of definitions for cyber risk. You have, of course, to know exactly what is the list of name, the acronyms, and what they mean for all these machine learning things, okay? So taxonomy. Taxonomy, maybe a small story here for my taxonomy. So I will say that some years ago, there is this question of the central bank to check if they have to introduce or not something equivalent to the Bitcoin, okay, but managed by the central banks, okay? So this is called CDVC, digital currency, okay? So you know, for instance, that maybe Finland has tried to replace 2 days. After 2 days, they stop. Okay, so the idea was to suppress all the coins, the banknotes, and this kind of thing. Okay, but it has been tested during some times in Canada. Okay, it has been tested during some times. Officially, last year, the Bank of Canada has said you don't have, when you have a presentation, to speak about CBDC. This is completely forbidden. We are no longer doing CBDC, this is finished, and you don't want to mention. Okay, so but here I am in France. So I mentioned, so no longer CBDC in Canada. But you have in parallel some surveys of Stat Canada, okay, for digital device, okay, which is to know if people are able to understand what are these electronic things, I will say. The idea was to, in particular, to focus in some category of people, for instance, the native in the north of Canada, or poor people, or this kind of thing. So they have done the survey, but what has been seen is that digital device was also a problem for the boss of the firms, okay? Not only for poor people, a lot of people don't understand. Maybe they know some names, but they don't know what it means, okay? And so you have another survey, okay, which is more oriented on cyber risk, to know now if I understand what is cyber risk, what we are doing. Okay. And so this is not, the questionnaire is not so good from a survey point of view, since in general, when you have such questionnaire, or people are not understanding more than five alternatives simultaneously. You can see that we will have maybe 8 or 10, but we know that we have a problem to try to classify the different types. And so you can see here, so we don't know, up to 3. So, but this is an ID. This is a kind of potential dictionary, okay? And this is with the idea that after we will have to select in some sense, okay? So you can see some acronym automatically, DOS, DDoS, okay? But maybe we will not continue. You have also improper usage of computers. Maybe some people are not using it the right way simply, okay? You have this kind of thing, which is very important. Okay? It was the same at the beginning for finance. You have survey to know if CEO of different banks know that the risk exists on financial markets. Here, this is the same kind of thing. Do you think that you are concerned or not? Okay. So this is not the sentiment by the media, this is the sentiment by the survey, okay, which is something different. And after, this is an idea of, even if they have seen some cyber attacks or some incidents, okay, do they report them? And you can see this is very specific here, since we don't know what they are doing. And maybe the people deciding of a survey have in mind that they have missed some possible thing. This is why you have a big or here. This is they can put something, okay? And of course, you can see reported. So of course, a lot of them are not reporting, which is the problem, and we cannot ask directly to them if they have reported or not, okay? But after you have, how do they know that they have an incident, okay? Maybe they don't know by themselves. And so you can see here a lot of connections. This is why networks are very important, okay? And you can see that maybe this is another firm, a partner, that will detect and that you have been attacked since he has first been attacked, okay? Or somebody else, okay? The police, simply, and so on and so on, okay? So we have a problem, okay? And here, this is the kind of survey, typically surveys, in order to have some ideas of terminology that we can have, how to define what is a cyber attack, how to define the names for the different types and so on and so on. It's all right? And here it continues. It's not a good survey. You can see here you have 12 possible answers. We don't know how to call them. Okay? But this is very natural. But we are at this level currently. Okay? So now we'll have some equations somewhere. Okay? So I will have time series of occurrences. Okay? I will, in fact, at this level, in this section, they are aggregated. Okay? That is, I have different types of attacks. You will see two types of attacks in the application, two types of attacks, and I am counting the number of attacks at a given period t. So I have two time series of count variables. So this is the beginning. In general, when you have count variable, the value are 0, 1, 2, 3. Okay? This is a very specific structure. So the usual model in machine learning, even with a recursive form, are not able to treat discrete variables. Okay, so we'll have to treat discrete variables. The other thing is, what is our purpose here? Our purpose is to analyze the predictive distributions, how to predict the future counts today, but this is more complicated than that, you will see. You are not simply interested in predicting what will be the future counts tomorrow. We will also be able, at the same time, in a coherent way, to predict tomorrow, after tomorrow, after tomorrow, and so on and so on. Okay? So a kind of term structure of predictive distributions. Not only term structure of predictive distributions, but also how to update at the same time the term structure of predictive distributions. So the updating also. So updating is very natural, okay? Since in this kind of machine learning, here you have time series, but you will see later on, or this is related with backpropagation, we are estimating online, okay? Each time new observations are arriving, you update the estimator also. So we will have also to update each day. This is not the day here, this is the month maybe. You have to update here your model, okay? And so this is online things at the same time. All right? There exists some method with recursive thing, with the right form in order to apply backpropagation. This is the one which is called normalizing flows. Okay, I don't explain what it is. It is not really appropriate here. It is not really appropriate since, in fact, it tries to update directly the densities. So here the conditional densities. What is known in the finance literature for pricing is that it can be easier to update the moment generating function via the densities. And so, in general, here you will see it will be done by means of a moment generating function. So moment generating function, this is what is called log Laplace transform. So don't be afraid, okay? We are just predicting, in fact, exponential transform, you can see, of the risk. It can be multivariate risk. It will be bivariate risk in our case, with the two components that are the count of the cyber attack of two types. The equation which is below seems very complicated, but this is interpretation that we will see after in another way, explain how you can decompose the risk at horizon h as a sum. This is a measure of risk at horizon h. It depends on you. This is a functional measure. We are estimating function, be careful. And it is explained how it can be decomposed into the updating of this risk measure at all intermediate horizons. Okay. You have to select, this is for any u, and so But what is important is the following thing. Okay? You are in an insurance company. In an insurance company, very often, we don't price in the same way as in finance. Okay? The basic pricing is to, I don't know how you call it here, risk-adjusted, maybe Swiss premium, or I don't know what is your name, but in fact, you introduce the utility function. Okay? The utility function, for instance, here, in the one-dimensional case, and you can see this is the Cara utility function, constant absolute risk aversion. And so after, you have this formula in order to price, to value, okay, your risk. Okay? The U as an interpretation. So we can see that now we try to explain what are the interpretation of what we are doing. Okay, this is a risk aversion. Depending on the risk aversion that you have as an insurance company. Okay. So you can see, be careful. Okay, maybe in your class, in the basic class, maybe it is said that for pricing in insurance company, you have to be neutral. Okay, you don't have to take into account this risk aversion since you can average. Okay. No, you cannot average since you have systemic factor, a lot of systematic factor due to the connection. Okay, so you cannot do that. Okay, so be careful here. Okay, but in fact, the decomposition that I have is simply a method of evaluation, which explains how the risk premium of the asset can be written as the sum of the difference of risk premium of the forward contracts. So now you can see the different types of contracts. Okay, this is contracts on counts here. After we will see contracts at the individual level, but here this is on counts. And so you can see that you have this formula, which is in fact now with interpretation of no arbitrage formula. Okay, and then you can decompose now to see what are the consequences of the prices. Okay, it's all right. Now we have to choose our model. Okay. So this is what is called an affine model in finance, or compound autoregressive model. So it was introduced in 2006, around this kind of time. The thing which is important is that you can see that it depends on some functions. This is particular kind of distributions. Okay. What is important, this is very strange, is that. So what is important? Fact. I think what is important here is the small composition. The small composition, this is what is very important to apply the backpropagation algorithm. And so in fact, you can compose like that. You can see that we have a kind of formula which can be used for any age. So you have a coherency of a prediction and this kind of thing, okay? And so you will have closed forms. So this is very important. You will have both closed form for the conditional distribution at any horizon for the updating of predictive distribution, but also if you are introducing the parameter in the right way, it will be a recursive system for which you can apply the backpropagation algorithm. Okay. So you will see the kind of model that we have. Okay. So here these are the data. Okay, so this is the basic, the only database that is used by academics for the moment. Okay. They don't have all the attack. Okay, these are simply attacks that have been reported. You can see to Attorney General. They concern in general public firms. We don't know exactly what are public firms like the hospital and this kind of thing. Okay, so and you have different type of attack. You can see here two types of attack. We will work on this kind of attack. An attack from external, outside party, or malware. So the malware, of course, can be introduced in several computers simultaneously. This is why it is very important to have this connection. And you have the other one, which is from inside. Okay, inside you have to check. Okay, employee, it's okay. Contractor, this is another firm. Okay, so this is the other firm. You have another firm, and you are connected with its system, and you have a problem. So maybe these are not very well clustering, but this is a clustering in the database. Okay, we expect, of course, to have something which has a better interpretation for our application. Here, this is more, since this is Attorney General, this is more with criminal terminology. You have a data. Okay, so you have in fact four. Here you have 4 types, and we are interested in you can see the hack and the breach due to insider. So different types of attacks you can see. You don't have a lot. Okay, so if you have in mind that you have several million of attacks during the week, maybe this is not the case if you restrict you to some particular sector of firms, or if you continue to decompose by category of attack, of course. So the idea is to decompose, okay, progressively when you have more data in order to continue to have accounts, okay? And of course, more data. Of course, when you have count variable, we have in mind Poisson process, but the Poisson process has some difficulties. The Poisson, the mean is equal to the variance, okay? And here you have some difficulty. The variance is not equal to the mean, you can see, which is rather usual. And also you have a lot of zeros. Since you have several days in a given sector, during one you have no attacks at all. So we have to take in the model both this over dispersion and the fact that you have overweighting on the zeros, okay? So in some sense, what I am saying is that the big attacks are maybe a rare event, okay? Okay? But rare event can be costly. I am just considering 0, 1, be careful. How is it written here? How is it written here? So here it is written, so I will go slowly here. It is written as, you can see, a measurement equation. So I have my 2 counts, y1 t plus 1, y2 t plus 1. And I write them following Poisson that depends on intensities. You have some intensities that are specific, xg t plus 1, and you have some specific that are common, okay? So the connection is by means of these intensities, okay? And so you can see this is a model which is a model with several layers, okay? So we start to see the layers. In the usual terminology, this is a recurrent neural network, since you have, of course, time, and at each time, you have another layer. The inside layer at period t, you have 2 layers. You have a layer for the idiosyncratic stochastic intensity and another layer for the joint stochastic intensity. You can have the impression that you don't have a lot of parameters when you compare to what is said in the news of the 3 billion of parameters. No. This is just since you are working with 2 series. Okay? If you are working with 100 series with 4 categories, this is 400. Okay? The number of parameters, for instance, you have a pairwise parameter. This is 400 by 400. This is 160,000 parameters. Okay, so very easy to increase the parameters with the problem corresponding to the fact that you have too many parameters, but this is something else. So very easy to have a large number of parameters. So this is not a big thing. This discussion on the number of parameters is artificial and not intelligent at all. So this is the artificial, not intelligence. And so what is important is that you have specific form of the Laplace transform, and then you can apply, okay, this kind of thing, and estimate by back propagation. Okay, so this is here. And so you can see what is arising. So these are the prediction. Okay, so just the prediction here. So you can, the prediction will depend on the risk aversion that you put on the two different types of attacks, and will depend on the current situation. And so you can see here the total, okay, and the repartition with horizon. So the 10 next periods to see what is arising. Here we have the impression that this is almost the same, but you can see we have taken the same values, current values for the observation of counts and the same level of utilities. But if you are considering now different levels, then you see that this is not the same, okay? And so this is how to predict, to approximate all this predictive distribution together in a coherent way, right? So just to give you an idea. So this is what is called an AFSNN, a fine feed-forward stochastic neural network. Okay. Now, just to finish, at the next step. The next step, there is a difficulty. So this is just to recall you what has been done at the beginning for derivatives. What has been done at the beginning for derivatives, it was with quantitative variable, a return. And so after we consider a function of a return, non-decreasing function, non-decreasing convex, sorry, this is for losses. Here, this is an insurance company, this is in terms of losses, okay? And so we were interested in this kind of transformations, okay, which is kind of utility function written for losses. And mathematically, we know that they are convex cones, and they are convex cones, and we know that these cones are generated by some things, by some basic functions. And these are these basic functions that have been used, okay, to construct the derivative markets. The first one is an indicator function. If the return is larger than, so this is if the loss is larger than, then you receive 1. If it is smaller, 0. Okay. This is what is called digit derivative. The other one are the usual European call. Okay. The problem that we have here is that now this is written on sets. This is written on sets, and on set, this is more complicated. Okay. Since this is the only ordering on set is the inclusion, and the inclusion is a partial ordering, not a total ordering. But nevertheless, it is possible to construct something which is equivalent to a kind of increasing function of set, or convex function on set, something like that. This is not exactly the same definition, but after you can say how they are generated. And the idea is, of course, to introduce derivatives whose payoff is written on this kind of things, okay? Similar to what exists. So this suggests two types of basket derivatives written on a set of firms, either tranches, okay? So if you consider a given S, okay, a given subset of firms, I don't know, you put meta, 3 firms like that, and some of them can be attacked. Why not? Okay, they can be attacked, and after you will see which one among the three that were at the Trump reception, okay, which one has been attacked, how many have been attacked, and so on every day. Okay, and so after, what we have to do is to consider these different pairs and to see if it is possible to price them. Okay. So you have some formulas. I will not discuss a lot, but you can see here, you can have first a CDS written on one firm, firm 1. On CDS written on 2 heads, 1, 2, as a kind of life insurance written on 2 heads, okay? You and your spouse, okay? This is the same here. Or on 3 heads of the same sector, since you think that they can be connected. And of course, this is not since you know what is the value for each head that you have a value for the 3 of them together, okay? Since you have a lot of connections, and we have to learn about the connections. So what is interesting is the following things. So this is this law of determinantal point process. Okay. What is known is that considering a random set S, which is the firms for which you have an attack, y I equal 1, the variable are binary. Of course, this is a random set, and it is equivalent to model the distribution of a random set, or to model the distribution of n binary variables. Okay, the n is large. Now this is firm by firm. Be careful. Now this is several 100,000 firms. Okay, this is why this is large. Okay. What is interesting is this kind of model, which explains how to replace the number of parameters in the unconstrained model. This is 2 power n, which is very, very large. This is always what is done in this machine learning literature, by something about the n square, okay, which is much smaller. And so here, this is a model that explains, due to a property of determinant, that you can maybe define a discrete distribution of binary variable. You can see this is the PS, by taking simply the ratio of the determinant of the minor, principal minor associated to this subset divided by determinant of identity. And what is important is now, this is the basic one, the G plus is the equivalent of a cumulative distribution function, that is the one that is used to price the digit derivatives, okay? So I will not discuss this kind of thing. So after you have different payoffs, and what you have here are the different types of derivatives, and corresponding to the different type of derivatives, the theoretical closed form formula, okay, corresponding to the price of these derivatives, okay? And they are simply computed from the sigma matrix and so on. So you have just to estimate the sigma matrix, which is replacing the usual sigma in the Black-Scholes, and you have some other closed form expression that are here that can be used if you want to try to create these derivative markets on the equivalent of CDS or more complicated things based on the random sets. So brief overview. So this is not easy, okay? Keep in mind, we have another, just before this risk, we have another one, which one, the transition to zero carbon. Even just for the taxonomy for zero carbon. So it starts maybe 4 years ago. The deadline to have a taxonomy has been reported. So it takes, just for a taxonomy, which is used in order to create the database we have. It takes a long time. It will be the same year. And of course, if the ADEM has no fund or diminution of the money it receives for the government, as you have seen, it will be a much longer time. Okay. You have also, you don't have the equivalent of the ADEM, but you have an equivalent at the European level to try to have a taxonomy for cyber, the same at the US level. But of course, US and Europe have to be coordinated to have the same kind of taxonomy, the same time of constructing the database, and so on and so on. It's all right?
So my favorite question, do we have questions in the audience? So, no? René, you have one? Okay, great.
Yes, your analysis reminds me a lot of credit risk. There are a lot of similarities. So in what sense cyber risk is distinguishable from credit risk? Maybe you can.
Yes, so the main difference, except that currently we don't have data at all, something like that, but this is, so. No, the main difference is the network. Okay? That are the network effects. So we cannot do as we are doing for credit risk, For credit risk, we can do something. Of course, we know that we have separated systemic risk and this kind of thing. But for the CDS, now this is just the 0-1. Okay? After you have to consider the severity, this kind of thing, but just for the 0-1, in general, they are assumed independent. But here, it is very, very important to have an idea of the connections. And this is the problem. So now we have to work directly with this kind of multivariate distribution on by 100,000 firms with a structure which is simplified somewhere, but with a connection. And I have to try to be able to estimate the connections, okay, before evaluating the risk, before pricing. So this is rather different. This is why this is very different. And this is why this is network, clearly network. Okay? So of course, you have also a part of the literature on this kind of thing that focuses on the observation of a network between the computers, okay? And solve the risk of this kind of thing. You know, for France, for instance, that some months ago, so this is not the same. For credit risk, what we know is that we have what is called systemic firms, systemic banks. This is a bank with a lot of connections, small and this kind of thing. Here we have the same kind of thing, but difficult to see. If you remember some months ago, you have an attack on a very, very small firms. The very small was the one by which all the data were transferred from all the doctors to the institution that have to reimburse all people. And they take all the data. It was a very, very small. And so you have two ways of trying to have this knowledge of this network from the data. If you have the data ex post, you will have there is a risk at this point. Or simply checking all the things, all the connection and all the codes. Okay. But this is the main difference. This is a big one. This is a big one.
Other questions? So just a comment. So there is a kind of balance to find between we need data sharing in order to improve the performance of all the LLM models, all the machine learning models. We need people share data. And on the same time, we have cyber risks. So how to balance between the two objectives? So because in order to improve or in order to launch machine learning in many sectors, we need to find a way to share data.
We have when I am sharing data, I'm not saying for the moment sharing the code, the token. Okay, this is sharing data on the attacks they have. Okay, this is the same kind of thing as for instance, for credit risk in the current supervision in general. In France, at least in France, we have to provide, for instance, to the central bank, okay, a minimum of data. Okay, the data have been standardized, and all this kind of data, these are not the complete data. They don't have to provide the detailed one, but a minimum of transparency, and they put together this kind of thing, okay, and they can work on this common information. So you have always this idea that you have a kind of common information that can be used by all people in order to train their model and this kind of thing, and which is clean somewhere, okay? And that is standardized. Okay? But they are not saying, I have been attacked since, or I have done this kind of thing completely crazy. Okay? You have just to say, this is this type of attack.
Okay, thanks.
So this is the limit of transparency that they have to share information, yes.
Okay, so thank you a lot again, Christian. So now we are welcoming our last speaker. So Dasheng, you are the last but not the least of our speaker.
Your watch? I didn't.
Yes, I have a cyber on my
Sorry. Okay. All right. It's my great pleasure to be here. Thank you so much for having me. So I guess the technical level of a technical talk is different in US and in France. So my talk will be technical according to US standard, but it's going to be a general talk in France. So there will be no formula from my talk. I guess that's good for the last talk of the day. All right, so today I'm going to tell you something about applications of machine learning in asset pricing in particular. And we'll talk about, the rise, the breakthrough, and limitations. All right, so just a brief disclaimer. This presentation is going to be an overview of several papers of mine on this topic. And it's going to be a very biased survey, as you can imagine. If you're interested in a slightly more balanced survey on this topic, you can read our book. All right, so let me start with the rise of the machines, right? So according to a recent paper, which actually summarizes Jing Fama's work, and his presentation in the Nobel, laureate event. So the two pillars of asset pricing. In this paper, Jing summarizes, two important components of asset pricing, which he contributed to. The first one is, of course, market efficiency, which we all, have heard about it, right? So one kind of important implication of the study on market efficiency is that we know that the expected stock returns are actually time varying. All right, so so there are certain predictors that would help us understand market return tomorrow or next period, and with those predictors we could design a market timing trading strategy to long the market at the right time. Now, second pillar of asset pricing is to design or to find patterns that explain the cross-sectional variation of expected returns, right? So, I mean, we would like to understand why IBM earns a higher expected return than maybe Apple. Okay, so and for this work, Jing has contributed, Fama French 3-factor models, and later on revised it to 5-factor models. So there's a huge literature trying to explain the variation of expected returns. So the commonality between these two pillars is the word expected returns, right? So measuring expected return is fundamentally a problem of prediction. All right, so my talk will be mainly about prediction today. All right, so now if we were trying to make predictions, as the previous speaker has explained, maybe we should be looking at machine learning. So what is machine learning? So from historical perspective, machine learning is simply be something that you can use to, for instance, play the game of checkers, the game of Go's, but a modern view of machine learning, at least the view that we're taking here, is that machine learning integrates three important components. All right, so statistics, domain knowledge in the form of big data, and also some computational techniques like optimization and algorithms, etc. Once you have the three components, you can call yourself doing some sort of machine learning. Now, why it's a good idea to apply machine learning for asset pricing in particular, for predicting returns? Well, first of all, there's lots of explanatory variables the profession has accumulated over the past few decades, right? And many of these variables are actually highly correlated, right? So think about, volatility, risk, liquidity, size. So these variables are highly correlated, they're close cousins. So it's kind of difficult to separate their individual influence on expected returns, and there are a lot of them. Okay, now in addition, economic theory unfortunately cannot always help. In fact, many of these predictors have economic theory behind to support their presence. But we still have like lots of such variables, and we don't have a very good idea which variables are most important compared to others. In addition, structural models in economics are fairly rigid because we like to use structural models to have closed form and derive some insights. But it's not a good idea to take structural models directly to data to predict returns, and the results are typically not very good. So in other words, the dependence of returns on explanatory variables could be highly nonlinear, very complex, and this is exactly what machine learning are good at. All right, so given what I've said, probably it makes sense to use machine learning, but has machine learning been used before? My answer to that is yes, but perhaps without knowing or without emphasizing it. So at least the spirit of machine learning has been used since the very beginning of the profession. All right, so for instance, in asset pricing, we have used lots of tools such as dimension reduction or variable selection, but without really, emphasizing it, right? For instance, we're focused on explaining portfolio returns instead of individual returns because of the benefits of dimension reduction and also averaging out idiosyncratic risks, right? And we also kind of select 3 variables, value, size, momentum, or value, size, market beta, to explain the cross-sectional variation of expected returns. And this is literally a variable selection. All right, so Fama French variables are example of variable selection. They selected the 3 variables from thousands of variables they could have selected from CompuStat or CRSP data sets. So the key difference between machine learning and human learning or economist learning is that economists are using economic theory or incorporate economic intuition or some kind of narratives into variable selection and dimension reduction. Versus machine learning can be actually totally let the data speak, but we are all kind of using some sort of prior, or you can call it regularization in machine learning terms, to reduce the dimensionality, to make this problem something that we can solve using simple regressions, for instance. All right, so given these kind of thoughts, maybe we should be thinking about embracing machine learning, modern machine learning techniques in asset pricing and see what's going to happen. All right, so around 2018, and motivated by the success of AlphaGo, my co-authors and I wrote a paper trying to compare lots of machine learning techniques to predict the cross-section of returns on a monthly frequency. All right, so we look at ordinary least square with 3 variables informed by theory as the benchmark, and we also tried a bunch of unsupervised learning, PLS, partially square, principal component regressions. We also tried supervised learning like lasso or ridge or their kind of combination, and we also tried some non-parametric method, generalized linear models. And we also tried, fancier, machine learning methods at that time. For instance, random forest or gradient boosted regression trees. We tried all these methods, and we started to find some evidence that these nonlinear models, the models that capture nonlinearity and the interaction terms, can potentially outperform. Now, we could have finished this paper, 2017. But we decided to try neural nets, right? So neural nets at that time was a hot topic, and this was exactly the algorithm, AlphaGo and many other advanced machine learning methods were based on. So we spent a year learning neural nets, and finally realized that it's a very cool non-parametric approach, which very different from the traditional view by econometricians in 1990s about like a parametric neural network model, right? So we kind of treat it as non-parametric method, and we're using the cutting edge way to optimize it, and we design it in a very efficient way to kind of take it to the data, and we find substantial gains of using neural nets over all the other existing methods. Right, so on this plot, we're showing you a cumulative return of a trading strategy, right? So at each month, we use different methods to predict individual stock returns next month. And then we're gonna long the stocks that are having the highest expected returns for the next month. and short those stocks with the lowest expected returns. All right, so the positive axis shows you the positive, the long side of the cumulative returns, and the red curve is the near nets, right? So as you can see, it has the highest expected returns, of this trading strategy. It beats all these other strategies. Now the negative axis shows you the short side, and the lower the better. And again, you see the near nets does the best. Versus other approach cannot compete with that. All right, so with this evidence, we kind of conclude that machine learning has a lot of potential to help us, for investment purpose from practitioners' point of view, and hopefully to help us find some kind of informative variables, later on to do some interesting economics. All right, so one potential critique we were struggling with was the black box nature of neural nets. Right, so imagine if you wrote a paper at that time just trying to sell neural net alone, you will be in trouble, right? So nobody would believe us. So this is partially the reason we like to compare it with all these existing methods for which we know very well their statistical properties. And we find out that these approaches, they select the same type of variables. All right, just the neural network also select the same type of variables. It's just that neural network allows kind of a more flexible functional form, better optimization, and finally stronger performance. So by the comparison, we can kind of learn the same kind of insights across different approaches, and that gives us a lot of confidence that neural nets is no longer a completely black box to us. So that being said, it's probably a good idea to kind of clarify what interpretability means, to the profession, because we have heard about critiques of black box, issues with interpretability all over the place. So what do we mean about interpretability, right? So it's a highly relevant and expensive topic in AI, right? So there's a lot of work devoted to it. In particular, more than 5 years ago, there's a lot of work on it. So I think there's at least 3 perspectives we should, talk about, today. Right, the first one is a statistical perspective, right? So interpretability from statistical point of view means, what kind of functions can neural network approximate, right? So suppose the data generated by a fairly complicated data generating process, are neural network capable of explaining these functions? And how effectively can it learn, right? So these are kind of statistical questions. To answer it, you really need to kind of dive into optimization and statistics altogether to have some good idea. Now, around 2018, we don't have a very good idea about it, and the field does not have a very good idea about it either. We did lots of simulations, but in the end, we managed to convince ourselves that we're not doing something crazy. Now, 5 years later, we started to see lots of progress, and by now we know very well, at least for supervised machine learning, what are their statistical properties, right? So supervised machine learning using neural nets, what are their statistical properties? And we know that very well now. Okay, so I don't think there's any kind of big issue about interpretability from that side. Now, from algorithmic side, there's a lot of problems. Right, so for instance, you are maximizing a highly non-convex function, and how can you guarantee that your algorithm converge, or the point that your algorithm converge, and how good that point is, right? So it's not clear. And in particular, to optimize these complicated neural nets, there are a lot of tricks that you have to use, such as batch normalization, dropout, and Adam. There's a lot of tricks that you have to use in order to achieve very good performance. And this is where I think, where the part that really needs more explanation, right? So theorists needs to work harder to kind of help us understand the properties of these optimization problems. Now, from the economic side, I would like to argue that neural nets is not more difficult to interpret compared to linear regression with many covariates. So in other words, the black box nature from economic point of view is determined by the nature of the problem itself, right? So the economic problem we're trying to solve with is like, there are thousands of variables that could potentially influence Y, right? Even if you're running a linear regression, it's impossible to kind of explain the marginal impact of one variable. right? So we should not blame neural nets being the one that is, black box from economic point of view, right? So, if you want to show me which variable is more important, I can do that as well for neural nets. Well, there are a lot of other perspectives on interpretability from regulatory perspective, legal perspective, and then et cetera. So I don't have time to discuss them now, and I'm gonna continue. All right. So that's kind of the story of the rise of the machines from in the literature of asset pricing. And from then on, we decided to move on and trying to apply machine learning for alternative data. If there is anything that you must use machine learning, it is alternative data, right? So at the time we tried to think about image data and text data. So let me start with the image data. All right. So there were a lot of excitement about using satellite images to look at a Walmart parking lot, or to keep track of to track the location of the oil tanks and things like that. We don't have that data. But we can actually have some interesting image data, or at least we can use image to do something. So here's an example. All right, so around 2000, there was a lot of discussion about technical analysis. So one reason people believe technical analysis still survive is that at that time is that pattern recognition was one of the few repetitive activities for which computers do not have an absolute advantage. For those of you who are not familiar with technical trading, it's just like reading some kind of charts or using price and volume information to predict returns. So that's kind of technical analysis. So no fundamental variables from accounting, etc. All right. So taken from this quote, we realized that after 20 years, probably we could revisit this question, because computer vision now has actually achieved a superhuman or ability to kind of recognize objects, right? So do we still have technical trading? Can technical trading still work? We kind of feel like it is possible, because if you think about a human trader who can more readily detect patterns in images, like myself, I would be able to kind of look at the image and get some idea about what's going on with the stock, at least better than just give me a bunch of numbers, right? So if we can imagine that human beings are better to recognize patterns than numbers, maybe there exists a statistical model that can do that as well. Okay, and that was kind of the motivation. Now here is an example, right? So this is like a technical charts. Okay, a technical trader would be able to read the open, high, low, close prices and the moving average lines in blue, and also the bottom like volume, bars. They would be able to actually make a prediction about what's going to happen, at least up or down, for Tesla stock tomorrow, right? So we're going to kind of try to do the same thing. Now, fortunately, this is not really something easy to do if you look at these charts, right? So these are kind of the most well-known patterns discovered by chartists. I have no idea, the left is going up or the right is going up. So they're like, exactly opposite patterns. In reality, it's also very difficult to kind of rely on these patterns because you don't know when the pattern has been, really formalized, right? So it's very subjective. All right, so which is one reason why financial economists, they don't really believe this technical trading. Well, so they don't believe these technical charts. In fact, technical trading has been documented by financial economists, right? So the most well-known technical signal by financial economists is momentum, right? So momentum is a very simple trading strategy. So you look at all the stock returns, right, for all firms. You can kind of look at their cumulative returns in the past 12 months to the past 1 month. So this 11 months period, right? So it turns out winners, okay, when those stocks which have a higher returns over the past 11 months tends to be winners in the next month. All right, so this is what has been documented as one of the very interesting technical patterns in financial markets, in equity markets. Now, why did you omit 1 month, right? So why did you go from the past 12 months to past 1 month to kind of sort stocks? Well, it turns out the last month it shows exactly opposite pattern, which is a reversal pattern, right? So winners of the last month tends to be losers next month. Okay, so if you want to build a long-short trading strategy, you should avoid the most recent months to form a momentum strategy, or you just use the last month to form a reversal strategy. All right, in any case, these man-made signals are very simple, super transparent, but it does not mean that they are necessarily interpretable, right? So we still don't have a very good, at least a very convincing argument from economics that technical signals have to be constructed in such a way. And why momentum has to be like past 1 year, not past 2 years, things like that. And even for the kind of explanation of momentum, there's so many different explanations. Some of those are actually quite interesting and kind of related to, some behavior economics. But in any case, right, so we do kind of believe there should be some technical patterns. In particular, if you think about predicting return within a month, the only variables you can use is pretty much just price and the volume, because fundamental information have not been updated at a very high frequency, right? So this is why technical trading is super popular among industry, participants. All right, so what we'd like to do is to look at whether machines can help us discover more complex and more profitable signals. Given that neither of us are interpretable, right? So let's just look at who can do better. So this is what we designed, experiment that we designed. So on the top you can see a 5-day image, black and white image that we created, a 20-day image or 60-day image. So it exactly contains the past returns, moving average lines, and the volume on the bottom. Okay, and then we designed the convolutional neural nets, which is the tool the computer scientists use to recognize patterns on the image. Okay, so how many patterns did we have? Well, turns out the green box on the bottom tells you how many parameters we use to construct patterns. As you can see, it's like 15,000 for a 5-day image, and even more so, for 60-day or 20-day images. All right, in the end, what we're trying to predict is what's going to happen up or down for individual stock when you are giving me a pattern like that, when you give me an image like that. All right, so let me kind of directly tell you, the accuracy, but in economic terms. Okay, I'm not going to tell you, hey, 52% accuracy or whatever. I'm going to give you like the trading strategy, Sharpe ratio, based on these predictions. I'm going to use the same kind of trading strategy like we described in the beginning, right? So if you look at the left top table, I5 means I'm using a 5-day image as an input. R5 means I'm going to predict return next week on a 5-day window, right? So next week. Okay, so based on this prediction, right? So basically each week I feed machines thousands of images for each stock, right? So for each stock I have one image, and I can get an idea of which stock is going to have the highest predicted return, right? So then I'm going to long those stocks and short the stocks that are going to have a low expected returns. And building this long-short trading strategy, I get a Sharpe ratio 7.15 annualized, which is crazy, right? So I only heard about these Sharpe ratios from top hedge funds. All right. So one reason you're not able to realize such a high Sharpe ratio is the high turnover. The turnover is like 700% per month. Okay, so to give you an idea, if you have a portfolio with 100% Apple, and you kind of sell all the Apple and buy 100% IBM, the turnover is 200%. All right, so 700% per month means we pretty much have to turn our entire portfolio every week. Okay, almost 200% every week. Okay, so you get a 7.15 Sharpe ratio. We're not trying to say that these numbers are realistic. These numbers are just trying to help you understand the magnitude in economic terms. So what's more interesting is to compare it with a weekly short-term reversal, the second to the last table on the first row. Okay, so like this one. This is a trading strategy based on weekly short-term returns, right? Basically, this is a man-made signal, okay, using exactly the same time window, 5-day returns. All right, so trade every week, and you can see the Sharpe ratio is only 2.84. Okay, much worse than the machine, but the turnover is actually similar. Okay, turnover is similar, 660%. So essentially, machines can do the same thing better than human, right? So we can actually get more predictability, higher Sharpe ratio at almost the same cost. All right, across the entire table, if you make the right comparison, let's say I20R5, the right benchmark for a 20-day image would be short-term reversal that use 20-day returns. You can see the Sharpe ratio is always much better using machines than using human signals. All right, so let me continue with another story. Okay, so hopefully I've convinced you that you could actually use images to predict returns or measure expected returns, and at least that short term. All right, so here we're kind of trying to look at texture analysis. So we did this analysis, in 2019. At that time, BERT was not well known yet, right? So we at that time, most people, at least on Wall Street, were using, bag of words representation of financial news. So basically, you take a news article, look at word frequencies, and compare those words with some kind of predetermined dictionary, sentiment dictionary, right? So based on the sentiment dictionary, you know which words are positive, which words are negative, and you calculate how many more positive words than negative words, and that's your sentiment score. Okay, so that was actually the leading or most popular approach back in 2018, 2019. So we took a look at this problem. We would like to understand what is a sentiment score, right? From econometric or statistical point of view, what is sentiment score? In addition, we do not like the idea of using some kind of pre-existing dictionary, right? So we would like to kind of, use machines to tell us which words are more influential, and that's what we did. Okay, so this is a theory paper that tried to explain, how accurate can you estimate sentiment score? How does that estimation problem or the accuracy depends on number of words in the dictionary, lots of other interesting summary statistics. So that helps us understand sentiment score really well. And then, the empirical analysis actually shows that if you look at for words that are positively associated with returns, so they're going to be on the first word cloud, the second word cloud, right on the bottom. And we can also find out words that are more negatively associated with returns tomorrow, right? So the benefit of textual analysis is so transparent. Based on these word clouds, you can see that the words that we discover match our intuition really well, right? So the word clouds on the top clearly include lots of negative words, and on the bottom clearly include lots of positive words. All right, so using this kind of machine-determined, sentiment words, we can build the same kind of trading strategy, long-short portfolios, right? So each day we long stocks with, higher sentiment scores and short stocks with low sentiment scores. And the black line is the long-short cumulative return, is the cumulative return for that long-short trading strategy. And the Sharpe ratio is a 4.3 something. All right, so pretty high. And the blue line here is ribbon pack. So for those of you who work on Wall Street, you must be very familiar or have been using ribbon pack, which was a leading news and it's a leading news analytics company, right? So if you kind of do the apple-to-apple comparison using their sentiment score, we actually did better. And then our strategy is fully justified, very interpretable, a completely white box. Their trading strategy is a black box to the customer, right? Because you do not know which part of their sample is training sample, which part of their sample is validation sample. You just have a bunch of sentiment scores. So that's why when you look at the performance based on their sentiment score post 2015, so it's not clear, is that really they're out of sample? That's why the performance is worse, or it's because the whole Wall Street have been using their scores, and as a result, the competition drives their scores useless, right? So we don't know that. So this is why having your own in-house model, is actually a good idea. All right. So I also would like to mention the red curve, which was using the pre-existing dictionary. All right, so the naive approach. And as you can see, both Ravenpack and our approach can actually beat that approach by a wide margin. Okay, so in fact, if you take into account the transaction cost, the LM approach is completely not profitable. Okay, earned a 0 Sharpe ratio if you take into a transaction cost, right? So which means that you could actually earn a huge Sharpe ratio with the system. All right, so that was the story around 2019. All right, naturally, once you have heard about large language models, you decided to maybe we should think about whether large language models can do better, right, than the bag of words or word-based approach. Okay, so we started working on this problem around 2020, using BERT and the Roberta, and then there's a bunch of larger language models available. Our paper is never finished. It's still not finished. So we are now using Llama 3 to kind of investigate our conclusions. So this table includes the first few large language models, and now this list is much larger, right? So as you can see, Llama and Llama 2 are open sourced, and GPT are closed sourced, right? Even though they're developed by OpenAI, right? So they're closed sourced. So what we did is we used this four highlighted models, right? So these are large language models. So we decided to use these models to analyze the same data set, the news data, and see whether they can do better. All right. So using large language models is not very easy, in earlier days, but we figured out how to do it. So basically, we download these large language models and feed them the news that we, for each individual company, and we actually get embeddings. Okay. In other words, we get a bunch of numbers that represent this piece of news. Okay. And then we run the regression, regressing the future returns onto these numbers to figure out the predicted returns. Now, this approach is very much similar to supervised fine-tuning for a specific task, right? So instead of directly using the pre-trained model, and this approach actually works really well. Okay, so let me just kind of give you some arguments like why we're doing this, right? So, according to economic theory, let's say market efficiency, right? So news should directly incorporate into prices. However, in reality, this process cannot happen at a lightning speed, right? So there has to be some kind of delay, right? So we got this idea from our conversation with hedge funds, right? We know that most of the large hedge funds, particularly the largest one, so when they are kind of allocating a portfolio of billions of dollars, they're not able to respond to news instantaneously about an individual company, let's say Apple. All right, because they also have to think about how to size IBM, right? So that's why what ended up happening is that these large funds, they typically calculate portfolio weights overnight and start trading from almost market open or a few minutes after market open and for a few days. And they also want to minimize transaction cost. That's why news would take some time to fully, incorporate into prices. Okay, so we would like to study this process, and now we're going to use large language models, and we're going to understand the actual contribution of news relative to past returns. Okay, and see, whether we can do better. All right, so the top left table shows you the following, right? If I'm looking at all stocks with news, okay, in the past week, and long those with low returns and short those with high returns. So this is like a weekly short-term reversal strategy, only using returns. You get a 1.58 Sharpe ratio. Okay, so pretty good, but not good enough. Now suppose I am using a word-based approach, right? So like system, the one that we developed, or the LM approach, right? So if we use these approaches to analyze, which words are more, which news have more positive words, in addition to the returns, we can get a higher Sharpe ratio, 2.61 and 2.79. Okay, so like using word does do better than just using returns. Okay, so using word in addition to returns does do better than just using returns. Now, how about large language models? All right, so if we use in addition large language models to analyze news, which does incorporate the context, you can get even higher Sharpe ratio, like 4.43, 5.0 for ChatGPT, and et cetera, et cetera. So it seems like using context, you can more honestly or faithfully represent news information, and you can actually do better than just using returns. So this is an example that I wanted to give you, but Noor has already mentioned it, right? So this is an example why large language models disagree with word-based approach. All right, so large language models recognize that this is a negative article. The darker the blue is, the more negative the sentence is. All right, but the bag of words and the word to back, those kind of leading kind of word-based approach, all believe that this is a positive article. Why? Because they see the word raise. Raise is more often associated with a positive news article. Okay, but the subject here is concerns have been raised, right? So this is why large language models can more honestly recover the sentiment. You might be interested to know what is the darkest blue here. So darkest blue is this company was not available immediately to respond. Okay, so that's actually a very negative thing. All right, so we actually analyze this more systematically, okay, not just kind of show you a piece of evidence. So we actually do the following, right? So we divide the entire news articles into two groups. One group without negation words and one group with negation words, okay? So if you compare the Sharpe ratio, the same string strategy for these two groups of articles, you find out that word-based approach, the last three, okay, the word-based approach, they can actually learn a higher Sharpe ratio for articles without negation words. They learn a lower Sharpe ratio for articles with negation words. Okay, so in fact, all right, so I mean, this could be due to a fixed effect, right? So meaning that articles without negation words just on average learn higher Sharpe ratios. But this is not true. Because if you look at large language models can learn higher Sharpe ratio for articles without negation words. All right, so meaning that word-based approach could have learned a higher Sharpe ratio, but because of their struggle with negation, they actually are not able to learn a high Sharpe ratio. All right, so we also try something more, more straightforward. So if you feed an article headline to a large language model and additional like a word-based approach versus article body, you find out that word-based approach, they actually do better with article headlines. Right, because article body will confuse this word-based approach. All right, so but if you're using article body, for a large language model, they would actually benefit from it. So in other words, large language model can actually understand the nuances in an article and be able to get even better, even sharper, sentiment results. So these kind of analysis kind of demonstrate the economic value of large language models, at least for investment purpose. All right, so you can more faithfully recover, the sentiment of news. All right, so beyond the sentiment, we have also done other work trying to analyze the topics discussed by Wall Street Journal, which translates to attention of the economy, right? So like, what kind of, what kind of news what kind of topics that policymakers or traders, they care about, right? And based on that, we can measure the state of the economy. All right, so I don't have time to talk about it, so let me just skip it. All right, this is kind of the development, of further development of machine learning, in asset pricing. So now I'm going to kind of talk about risk-return trade-off, which is an important topic in classical asset pricing. And here we're kind of trying to use machine learning ideas to deal with some of these problems. So let me just kind of give you one idea, all right? So, 10 years ago, right, so or 5 years ago even, right? So there was a lot of discussion in the literature about like which factors drive expected returns. All right, so there's so many of those factors proposed. Now, all these factors have some economic reasoning behind. And in the end, you kind of have a zoo of factors, or you have a zoo of factors, and you don't know like which factors are truly important. All right, what we discover is that many of these factors were discovered with a benchmark against the pharma fringe. So in other words, researchers find out that this new factor can explain phenomena or can explain expected returns that cannot be explained by pharma fringe. All right, so it turns out, it is possible that researchers are discovering the same phenomena over and over again, because they are all kind of, compare against the pharma fringe, which we know have a lot of issues, right? So they cannot explain momentum, they cannot explain some kind of seasonality and things like that. So in fact, if you choose the right benchmark, some of these factors discovered later should have been discovered, should not be a new factor. Because, for instance, seasonality can be explained by momentum, right? So if you use pharma fringe plus momentum as your benchmark, seasonality is not a new factor. All right, so then why cannot researchers always benchmark against the entire existing zoo of factors? Well, that's because you have hundreds of existing factors, and you only have hundreds of observations. So you have a kind of curse of dimensionality problem in your regression. And that was around 2019. We kind of write this paper using variable selection to select, truly useful factors as a benchmark, right? So, and then the new factor needs to pass this new benchmark to qualify as a new discovery. And this helps us reduce the zoo of factors substantially. All right. So this is about, if you know kind of the economic terms, this is about stochastic discount factor and the loadings onto factors. We're also kind of interested in risk premium, right? So risk premium is about, hedging, right? So suppose I would like to build, a portfolio to hedge macro risk, or build a portfolio to hedge climate risk, or GDP risk, right? So there's a lot of, macro or non-tradable risk that you need to build portfolios to hedge. And we kind of use machine learning to build these mimicking portfolios to hedge this risk. I'm not going to talk about this in details. Finally, in our earlier analysis, all we have done is to predict returns. Once you have predict returns, you don't know which part of the predict returns are due to alpha and which part is due to risk, the beta part, right? You don't know about that. So that was one of the critiques. All right, so then we kind of responded to it by writing a new paper that trying to kind of, decompose returns into the beta part and alpha part. And here we'll also use deep learning, and in particular, something called autoencoder. So it's a kind of a nonlinear version of PCA to explain asset returns. Now, this was a very cool, methodology. And at that time, we don't know how to, whether it makes sense to do it from a statistical point of view. And very recently, we kind of have finished the paper that explained the statistical performance of autoencoders. So for those of you who are interested, you can look at my website. All right. So the last part of my talk will be on the limits of the machines. Yeah, I have less than 5, right? Okay, very good. I'm just going to plan to talk for 5 minutes, okay? So I just want to kind of highlight one study, okay? So this study is about, can machines learn weak signals? So we know that, many of these machine learning tools were borrowed from computer science, where the signal-to-noise ratio is exceptionally high. Like if you think about vision problems, right? The signal-to-noise ratio is like 95% plus, okay? So, but in economics and finance, if you look at R-square, the R-squares are kind of have a spike around 0 or very, very small, because economics is really hard to kind of have very strong signals, right? So in fact, given the technology, the current technology you have, any new signals will have to be weak. Otherwise, someone else would have already discovered it. All right. So the question is, can machines help us discover these signals? Okay, so we know machines work well in strong signal settings, but do they work well in weaker signal settings? So in fact, right, so we can translate the problem of can machines learn weak signals to a question that is much easier to analyze, which is the following, right? So if you are applying a machine learning approach and you did worse than without any learning, then machine learning is not helpful. So which model is not learning at all? Just using 0, okay? If you just use 0 to make prediction, your prediction is always 0, right? But for low signal to noise ratio environment, 0 is a pretty good benchmark, okay? So my question then is, can machines beat 0 out of a sample? All right, so it turns out we find striking results. All right, so first of all, we find out that the optimal reach, right, which is a very classical old school, machine learning method, can actually beat 0. Okay, so in fact, if you have some part that is below the 0 axis here, it means that with a good tuning parameter, you can actually beat 0. Now, as you can see, for a very wide range of lambda, this reach estimator can beat 0. And with lambda become larger and larger, reach eventually becomes 0, right? So it's kind of makes sense. All right, what's more striking is that optimal lasso is 0. All right, meaning that if you try a lasso approach, which kind of encourages sparsity, regardless of what tuning parameter you're using, you're just always behave worse than 0 in the weak signal scenario, right? So this should kind of caution economists not to use or not to always kind of treat lasso as the model and least square, but to think about reach and others, as well, at least, because lasso is actually, you can prove that in weak signal scenario, lasso is not good. Okay, it behave worse than 0. All right, only when you choose a large enough tuning parameter, lasso becomes 0, and they become even. Okay. All right, so my last slide is about some kind of empirical evidence. We also have simulation evidence. We can actually show you that, any methodology that encourages sparsity, such as boosting, okay, or neural nets with L1 penalty, they will not do well in low signal to noise ratio environments. But in any predictors that encourage dense, or kind of averaging, like random forest or neural nets with L2 loss, they can actually learn very effectively. Okay, so this is kind of, this is kind of my final conclusion. So actually this sign is wrong. Anyway, so all right, so that's it. All right, so I guess we kind of show you the development and also kind of the limitations. Thank you very much.
Oops, thanks a lot. So questions? So we are all tired, but questions or no? So maybe people could benefit from this sort of. So I think that I have one, but just a small one because it's. So I am very impressed and by the fact that you use image to predict something. So this is something that I was very surprised by this part. So in some sense here you try to detect pattern, right? Mm-hmm. So this contains information from the past. Yeah. But when you speak about machine learning advantage, it's also to get signals from also weak signals from some other source than the market, right? Or maybe I'm confused. So in some sense, when you read newspaper,
right,
it's always the same question for me. So there is there are correlation between two events, but it's unclear about the causality of the. So for instance, the momentum, if everyone believes in the momentum, it's not very surprising that you observe momentum, right?
Absolutely, yeah.
Yes. So here in your machine learning techniques, how to disentangle the techniques which use the past, like this one, like looking at the image, at the patterns, right, and machine learning techniques which uses information somewhere in outside the market prices or the volume and all the market data.
Right. I mean, so this is a very, very important comment, right? So we had thought about it, but a very short answer to our question is that in our view, machine learning is just kind of, a predictive tool, right? That translates some kind of patterns, if any, to predictions, right? So Beyond that, it's really hard to see anything, right? So in fact, if you ask a chartist, they could always give you a story, right? But you know, how much credible, right? So how much credibility there is in the story is the question, right? So that's why we kind of completely give it up, right? So for this project, so you're right that we were very surprising because we believe you know, technical patterns should not be there, right? So despite you know, what we have heard on the street, they always kind of trade on technical patterns. I cannot find a hedge fund, particularly those relatively high frequency funds, right? They always trade on technical findings, right? So that's why we decided to kind of do a benchmark, right? So, but again, I share the concerns with you. We don't know like whether it's because of something else that caused these things to react. Yeah.
I just want to rebound on your on the what the chartists say.
Yeah.
Do you have a collection of what they say? I mean, like, is there a data?
Yeah, we do. So
but
we have a.
You could add that also to see, for example, if they add, you know, something to.
Very good. So this is partially why we are doing this exercise, right? So think about what we have achieved is we now can read any pattern, translate into return prediction probabilities, right? So then we kind of collected a list of chartist patterns and feed it into our estimates and see whether they're right or wrong, right? So guess what? You know, I think about some of these patterns are fairly close to give us a correct, you know, or positive. I mean, machines kind of agree with some of these chartists, like head and shoulder, for instance, right? So machines also agree with this pattern. So when you see this pattern, likely to have a, you know, upper probability. So what we did is we simulate the path, right? With this kind of trend, we simulate thousands of those paths and feed it into machines and calculate average up probabilities. We find that machines find it positive. Yeah. So for instance, yeah. So you can, so in other words, you can totally diagnose any patterns you like with this new machine.
But you have, just to come back on the head and shoulders, what is said about this kind of pattern in the Chartist method, and this is one of the critiques for Chartist, is the fact that at some point, all traders know that in fact you have this kind of head and shoulders.
Yeah.
And so they change their portfolio before the second one.
Absolutely.
And for the end of the second shoulder has disappeared from the market.
Yeah.
So,
right. So I think this may be why some of these patterns are no longer effective, right? So we don't find all these patterns, you know, meaningful. And some of these patterns we even find, you know, negative results, like completely opposite. All right. But keep in mind that machines are finding very complicated, you know, predictability, right? So it's not like, you know, we're confirming any. So like machines are kind of very capable, and they are actually also changes depending on over which window you train it. So I don't know how long these patterns will last, but at least based on our analysis, right? So we train the model and use it for a year. It seems to work well.
It's not exactly a question, but an observation, which is not totally surprising. Of course, we were partially aware of what you have been developing, but of course, over the last years, we have been looking at machine learning, etc., in order to try to extract from data other data. That is, I take some data which are available or not available or partially available, and I try to extract from that some other data and make some prediction. What is very interesting in what you have been doing, because it seems to be much more powerful than effectively this translation of data from data to data is from image and text to data. And this is the part which is, of course, is a game changer, if in fact totally, and it seems much more powerful, of course, and it's not immediately, comes not immediately to the mind, but in fact, when looking at it, it's intuitive. You have made reference to economists who were always since Edgeworth looking at graphs, because graphs are better understood by people and even by non-mathematicians. And of course, we are all looking at index. You were referring, for example, to the VIX and the economic policy uncertainty. Of course, it's something which is manipulating many things which are not totally clear, but which seems to be effectively relatively well correlated with even fine tuning of movements in the VIX. And it's something which of course asks for a change of axiomatic, because it seems to me very important, and probably for us in the insurance industry, we have been looking and trying to extract new data, many more data, for example, on natural catastrophe, etc., in order to be able to anticipate what may be the size of the natural catastrophe, but maybe you have to try to extract more text, more qualitative information, and transform them into data and predictions. Sorry,
Yeah.
it's just an observation.
No, it's a very important comment. Yeah, yeah, I agree with you. Yeah.
And take a picture to see if someone is in good health or not. So it's very difficult. Now, for the prediction of natural disaster, I think that satellite image is part of the important data. And I think these CNN methods are very useful.
Could be, yeah.
But what is very astonishing is the fact that you apply this idea of image recognition to predict financial crisis. Is a beautiful idea that has been rewarded, as I understood, but it's very good. So there are other questions, or maybe more related to your insurance business, or how do you imagine implementing machine learning methods in your daily business? I don't know. It may be something you are more.
We had one effectively, and we tried at some point in time, even with life. I remember with Emmanuel Plisson at the beginning of the COVID pandemics, because we were not knowing what was happening truly, because information came slightly later when we were confronted to a phenomenon which is a very quick one and developing exponentially. Therefore, at the time you are discovering the damage, it's largely too late. And then we turned to Google search, and in order to look how much people were looking to the word pandemics, COVID, etc., in order to have some signal from the text. And of course, we have seen until a certain point in time that there has been a good correlation.
Yes.
Thereafter, it was much more difficult, and probably it was too simple and to be really efficient, which would have developed the model as you did for financial markets.
Makes sense. Yeah, yeah.
So, thank you. I think that we can. All the participants. So I'm not very good with the mic. Thanks, Philippe and Zéine, all the team, Lynn, Marion. So, thank you for the way you host us, and see you soon for another workshop. Yeah. Thanks.
Thank you, Stéphane, to thank you, René, Noor, Christian, and Dasheng, because it was really illuminating, and I very much would like to thank Dasheng, who has made a transatlantic transfer in order to give us some very illuminating presentation. Thank you so much. We have a small cocktail for those wanting to.
Yeah. Champagne.
But not the US champagne.
Yes, the black one.
It's like
It's like technical people. It's not the same level. Yeah.